Some particles behave, some vanish, some return stranger than before. And what began as a meticulous search for a missing piece in a neat, orderly equation soon ballooned into something far larger, far more profound. It became a journey into a field that stretches through all of space, an invisible lattice underlying reality itself, and a particle so elusive that its very existence seemed impossible. The discovery that eventually emerged sparked worldwide celebration, yet quietly, it carried an unsettling truth. Physics, for all its triumphs, still lacks the complete story. What if the particle we call the Higgs boson is not the final piece of the cosmic puzzle, but merely the first glimmer of a deeper, hidden layer of reality? What if the mass it imparts to particles is only one chapter in a story that stretches far beyond what we have glimpsed so far? And what if the universe, precariously balanced on the edge of stability, is whispering secrets that we have not yet learned to hear? The Higgs boson solved one mystery, but countless others remain tucked away in the space between what we observe and what we assume we understand. The standard model of particle physics is often celebrated as one of the crowning achievements of modern science. Yet when viewed from the outside, it can appear as a curious, almost patchwork-like construct, a collection of interwoven ideas that aim to describe all known fundamental particles and their interactions, except for gravity, which stubbornly eludes its reach. At its core, the standard model is a framework describing how quarks, leptons, and force-carrying particles combine, interact, and underpin everything observed in ordinary matter. To a newcomer, it may seem like an elaborate cosmic puzzle, painstakingly assembled over decades of theoretical insight and experimental verification. But despite its name, it is not a single, elegant equation or a fully unified theory. Rather, it is a carefully layered mosaic, assembled piece by piece to match data collected from a dizzying array of experiments. Even so, it continues to succeed where other theoretical attempts falter, making predictions of astonishing precision and providing a remarkably accurate guide to the behavior of subatomic particles. In the mid-20th century, physicists faced an overwhelming deluge of newly discovered particles. Each upgrade of particle accelerators seemed to reveal an entirely new cast of subatomic actors: mesons, baryons, hadrons, leptons, and more. The list grew so extensive that some half-jokingly referred to it as a zoo of particles rather than a coherent system. The emergence of quantum mechanics and the formalization of quantum field theory prompted theorists to seek order in this chaos. Brilliant minds looked for patterns, striving to explain the vast menagerie in terms of a few fundamental building blocks and a handful of forces. Their efforts gradually coalesced into a structure that classified matter particles as quarks and leptons, and force carriers as gauge bosons. The standard model identifies 6 types, or flavors, of quarks: up, down, charm, strange, top, and bottom, and 6 leptons, including the electron, muon, tau, and their 3 corresponding neutrinos. On the force side, it names the photon for electromagnetism, gluons for the strong interaction, and W and Z bosons for the weak interaction. This elegant categorization allowed scientists to systematically organize subatomic data and make bold, testable predictions. Over decades of experimentation, each predicted particle was discovered, strengthening the model's credibility with every success. Among its most remarkable achievements is the precision with which it predicts phenomena like the magnetic moment of the electron, matching experimental measurements to a staggering number of decimal places. Each new generation of particle accelerators, from early colliders to the tevatron and eventually the Large Hadron Collider, pushed the standard model to deeper tests. By the 1990s and early 2000s, discoveries like the top quark and tau neutrino confirmed the model's robustness, yet physicists acknowledged that major gaps remained. Gravity, dark matter, and the precise masses of neutrinos eluded complete explanation. The model requires more than a dozen parameters to be measured and manually inserted. It does not predict them inherently. This incompleteness has driven theoretical speculation for decades, from supersymmetry, which proposes a hidden spectrum of partner particles, to theories of extra dimensions and grand unification. Despite decades of effort, none of these extensions have received decisive experimental confirmation. The standard model remains a resilient scaffold, capable of describing the observed universe with remarkable accuracy. The history of the model's development is itself a story of brilliance and persistence. In the 1960s, Murray Gell-Mann and George Zweig independently proposed the quark model, explaining the growing collection of hadrons as combinations of simpler constituents. Quantum chromodynamics, QCD, soon emerged to describe strong interactions mediated by gluons. Around the same time, Sheldon Glashow, Steven Weinberg, and Abdus Salam unified electromagnetism and weak interactions into the electroweak theory. The discovery of W and Z bosons at CERN in the 1980s validated these predictions and cemented the model's framework. Yet the standard model remained incomplete until it could explain how particles acquire mass, a puzzle solved by the Higgs field and the eventual confirmation of the Higgs boson in 2012. This discovery was celebrated as both a triumph and a reminder of the gaps that still exist. The standard model operates within the language of quantum field theory, where each particle corresponds to an excitation of a field that permeates all of space. Interactions occur as fields exchange force carriers or couple to the Higgs field, dictating particle behavior with stunning precision. Its reach extends beyond high-energy physics, influencing nuclear physics, astrophysics, and neutrino research. Deviations from its predictions are closely scrutinized, often leading to temporary excitement before being resolved as statistical fluctuations. Yet this same stubborn consistency highlights both the model's accuracy and the challenge of uncovering entirely new physics. Despite its elegance, the standard model is also messy. It cannot explain gravity, it relies on empirically determined parameters, and it introduces the Higgs mechanism as a necessary patch. Its mixture of elegance and imperfection exemplifies the iterative nature of scientific progress. Models are built to match data, refined over decades, and left to evolve as new discoveries emerge. Even after more than half a century, the standard model stands as a triumph of human intellect and experimental ingenuity, a foundational framework that underpins our understanding of the subatomic world. Yet beyond it lies a tantalizing question. What deeper truths remain hidden, just beyond the edge of what we can currently probe? The universe continues to whisper its secrets, and the standard model, for all its brilliance, may be only the first map of a far larger, more intricate terrain. The question of why particles have mass, why forces vary in strength, and why the cosmos is structured as it is, remains largely unanswered. Physicists continue to push the boundaries, building ever more powerful accelerators, refining experiments, and searching for subtle deviations that might crack open the door to the unknown. Each discovery, each anomaly, each incremental advancement is a step toward understanding a universe that is far stranger and more magnificent than any equation can capture. The standard model is not the final word, but it is a testament to human curiosity, persistence, and the relentless quest to illuminate the hidden scaffolding of reality itself. But that very symmetry seemed almost insistent, whispering that fundamental particles such as the W and Z bosons, or even the humble electron, should be entirely without mass. Yet experiments, carefully conducted and repeatedly verified, clearly demonstrated otherwise. The W and Z bosons, for instance, are surprisingly heavy when measured against the subatomic scale, far outweighing electrons and neutrinos. This glaring contradiction between the theoretical insistence on masslessness in a perfectly symmetric framework and the undeniable reality of massive particles emerged as one of the most perplexing puzzles in quantum field theory. The solution demanded that symmetry itself be broken, but the challenge was immense. How could this be done without dismantling the intricate architecture of the theory itself? One way to imagine the problem is to picture a universe governed entirely by a massless particle theory. In such a universe, all particles would travel at the speed of light, behaving like photons. But this hypothetical reality would be unrecognizable to us. Electrons, stripped of mass, would no longer form the atoms and molecules that compose matter as we know it. The familiar properties of chemistry and everyday materials would be unthinkably altered. Yet inserting mass arbitrarily into the equations would violate a crucial principle: gauge symmetry. This symmetry is far more than mathematical elegance. It underpins the entire structure that allows the theory to predict interactions at the quantum level. Maintaining consistency and renormalizability required a delicate approach. Mass had to emerge naturally without prematurely breaking the underlying principles that governed high-energy interactions. Early attempts at unifying the electromagnetic and weak forces, spearheaded by Glashow, Weinberg, and Salom, framed the interactions under the SU2's U1 gauge group. Their formulation elegantly merged the forces, but a key question remained: how could W and Z bosons acquire substantial mass while the photon remained strictly massless? Physicists faced a profound theoretical impasse. The breakthrough came through the concept of spontaneous symmetry breaking, a principle familiar in condensed matter physics, especially in the context of superconductivity. In superconductors, the electromagnetic symmetry is effectively broken, generating phenomena impossible under strict symmetry. Could a similar mechanism govern the fundamental particles of the universe? Spontaneous symmetry breaking occurs when the underlying equations retain symmetry, yet the vacuum, the lowest energy state, chooses a specific orientation, shattering the symmetry in practice. The analogy is vivid. Consider a magnet. Above a critical temperature, it has no preferred direction, maintaining perfect symmetry. Below that temperature, it spontaneously aligns, picking a single direction and breaking the symmetry without altering the fundamental laws. Transposed to particle physics, Peter Higgs and others proposed that a new field permeates all of space. Particles interacting with this field gain mass, while those that do not remain massless. This mechanism elegantly preserves the high-energy symmetry while generating mass where needed. Initially, many experts were skeptical. The notion of a pervasive field breaking symmetry across the cosmos seemed radical. The theory predicted the existence of a new scalar particle, later named the Higgs boson, whose discovery would be critical to validating the concept. Yet building an instrument capable of detecting such a particle was a technological dream decades in the making. While the theoretical papers appeared in the mid-1960s, the wider scientific community only embraced the idea in the 1980s and 1990s, spurred by the accurate predictions of the electroweak theory regarding W and Z bosons. Even with the Higgs mechanism, the origin of mass is not entirely resolved. Elementary particles like electrons and quarks have intrinsic mass, but composite particles, such as protons and neutrons, derive most of their mass from the energy binding quarks together via gluons. According to Einstein's E equals mc squared phrase, breaking a proton into its constituent quarks reveals that their combined rest mass accounts for only a fraction of the proton's total mass. The remainder emerges from the energy of the strong force. The Higgs mechanism specifically accounts for the fundamental masses of quarks, leptons, and W and Z bosons, but the bulk of the visible mass surrounding us arises from the dynamic interactions dictated by quantum chromodynamics. Without the Higgs field, quarks would remain massless, preventing the formation of protons and neutrons as we know them. Neutrinos add another layer of complexity. Initially considered massless within the Standard Model, experiments eventually revealed that neutrinos oscillate between flavors, a phenomenon only possible if they possess mass. This required a modification to the Standard Model, introducing a neutrino mass term. How this mass arises is still debated, with mechanisms like the seesaw offering possible explanations, but no complete solution yet exists. This underscores that the Higgs mechanism, while crucial, does not entirely account for the mass of every particle. Ultimately, the deeper philosophical question persists. Why does mass exist at all? Is it a mere feature of the universe, or does a more profound principle demand the presence of mass-generating fields? Symmetrical equations captivate physicists because of their aesthetic and predictive power, yet the universe insists on imperfection, on mass, revealing a subtle tension between mathematical beauty and the tangible reality of the cosmos. But the universe we inhabit is far from perfectly symmetrical, revealing a complex tapestry of forces and phenomena that differ dramatically depending on the energy scales we examine. At low energies, the electromagnetic force and the weak nuclear force display strikingly different characteristics, even though theoretical frameworks suggest they may unify under higher energy conditions. This apparent disparity is not a flaw in nature, but a reflection of a deeper principle: spontaneously broken symmetry, a phenomenon that allows identical underlying laws to produce dramatically different behaviors, depending on the circumstances. It is this very mechanism that gives rise to the mass problem, one of the most captivating and consequential puzzles in modern physics. Understanding mass is not merely an exercise in mathematical abstraction. It is central to comprehending why the universe appears structured and ordered rather than a uniform, massless void. The pursuit of this understanding required physicists to envision machines of unprecedented scale and sophistication. If the Higgs boson, a hypothetical particle predicted to mediate the acquisition of mass by fundamental particles, truly existed, it would only manifest at extraordinarily high energy levels. To detect it, colliders such as the Tevatron at Fermilab and subsequently the Large Hadron Collider at CERN had to be constructed with capabilities far exceeding those of previous generations. These experiments were not just scientific tools. They were monumental undertakings designed to probe the very foundations of reality. The search for the Higgs boson dominated particle physics research from the closing decades of the 20th century well into the early 21st, generating anticipation, hope, and a degree of apprehension. Failure to find it within a certain energy range could have implied a fundamental flaw in the prevailing theory, forcing physicists to reconsider the Standard Model itself and to entertain radically different approaches to explaining mass. By the late 1990s and early 2000s, the Higgs boson remained undetected, yet indirect evidence suggested a narrow window in which it could exist. Precision measurements of other fundamental particles, including the W boson and the top quark, increasingly constrained the Higgs mass. These indirect observations aligned with theoretical expectations, reinforcing the plausibility of the Higgs mechanism, yet the direct evidence remained elusive. The Tevatron came tantalizingly close, but lacked the necessary energy to deliver definitive results. The responsibility then shifted to the Large Hadron Collider, which began operations in 2008, bringing with it a mixture of anticipation and tension that electrified the particle physics community. When the LHC announced in July 2012 that a particle consistent with the Higgs boson had been observed, it marked a watershed moment in the scientific understanding of mass. The newly discovered particle exhibited behaviors predicted by the Standard Model, though additional experimentation was required to verify all its properties. Even with this breakthrough, fundamental questions persisted. Was this the only Higgs-like particle, or did a broader family of similar particles exist beyond the Standard Model? How did the observed Higgs mass fit with other theoretical constructs, such as supersymmetry, which had predicted different mass ranges? The discovery answered some questions while leaving others unresolved, illustrating that the mass problem is a multi-layered enigma rather than a simple equation. Mass itself underpins the structure of the universe. It governs the behavior of atoms, molecules, and ultimately the formation of stars, planets, and galaxies. Without the masses we observe, electrons would not stably orbit atomic nuclei, nuclear forces would not bind protons and neutrons in familiar configurations, and life as we know it would never arise. Understanding mass is therefore intertwined with understanding the very conditions that allow chemistry and biology to flourish. The quest to uncover the origin of mass is not purely academic, it has cosmic implications, revealing how subatomic phenomena dictate the architecture of the observable universe. The Higgs field offers a partial explanation, but it does not illuminate why some particles, like the top quark, are so heavy while others, like the electron, are so light, nor does it account for the minute masses of neutrinos or the unseen mass attributed to dark matter. This persistent uncertainty fuels both theoretical and experimental research as scientists search for patterns or principles that might unify these seemingly disparate masses. The problem of mass is therefore a driver of innovation, compelling the construction of ever more powerful accelerators and inspiring new theoretical frameworks. This journey illustrates the interplay between curiosity-driven theory and technological advancement. The search for the Higgs boson required decades of experimental development, culminating in the Large Hadron Collider, a 27-kilometer ring capable of accelerating protons to near light speeds and smashing them together with unprecedented energy. Within colossal detectors such as ATLAS and CMS, physicists sifted through billions of collisions, hunting for the fleeting signatures of Higgs decays. The challenge was immense. The particle itself decayed almost instantaneously, leaving only subtle traces in the spray of resultant particles. Years of painstaking data collection and sophisticated analysis were required before a clear signal emerged. In 2012, a signal corresponding to a particle with a mass around 125 gigaelectronvolts finally appeared, exceeding the 5 sigma threshold necessary to confirm a discovery in particle physics. Researchers remained cautious, referring to the particle as Higgs-like, until additional measurements confirmed that it exhibited the predicted interactions and properties. The discovery, while popularly sensationalized as the God particle, was far more than a media headline. It completed the roster of particles predicted by the Standard Model, providing the long-sought missing piece for explaining how fundamental particles acquire mass. This achievement earned Peter Higgs and François Englert the Nobel Prize in Physics in 2013. The story of mass, therefore, is not merely about a single particle. It is about the fundamental principles that shape our universe, the intricate dance between theory and experiment, and the profound consequences of seemingly abstract ideas. It is a story of global collaboration, cutting-edge engineering, and the relentless human drive to uncover nature's deepest secrets. While the Higgs boson answered crucial questions, it also opened new avenues of inquiry, ensuring that the pursuit of understanding mass remains one of the most vibrant and essential quests in modern science. However, scientists were quick to emphasize that the mere discovery of the Higgs boson did not mean that the grand puzzle of the universe had been solved. While the particle's identification marked a monumental achievement, it was both an ending and a beginning, a closing of one chapter in the story of physics and the opening of an entirely new, far more intricate one. For a fleeting moment, there was hope that the Higgs, revealed through the colossal experiments at the Large Hadron Collider, might serve as a gateway to uncovering phenomena that lie beyond the Standard Model. The tantalizing idea of supersymmetry, which predicts a host of new particles, seemed within reach. Yet, the universe proved more cryptic. Many of the particles that supersymmetry anticipated failed to appear within the expected energy ranges, leaving physicists both awed and puzzled. Some speculated that the Higgs might harbor exotic decay patterns, subtle deviations from the textbook predictions, or hidden behaviors that could point to new physics. However, meticulous measurements so far have shown the Higgs to be remarkably faithful to the expectations of the Standard Model. Its interactions, decay rates, and couplings with other particles have matched predictions with impressive precision. This confirmation was reassuring for the theory, but offered fewer clues for those seeking cracks in the framework that could hint at entirely new realms of physics. Even as the Higgs boson was celebrated, the deeper enigma of the cosmos remained untouched. Dark matter, dark energy, the minuscule masses of neutrinos, and the profound mysteries of gravity continue to elude explanation. The Standard Model, powerful though it is, remains silent on these cosmic scale puzzles. The elegance with which it accounts for visible matter only magnifies the absence of insight into the dark majority of the universe. The task of constructing a more complete theory is formidable. Any such theory must accommodate not just the particles we see, but also the unseen mass and energy that dominate the cosmos. Yet, despite decades of searches, no direct evidence has emerged for the new particles or fields required to fill these gaps. The concept of the missing piece in science thus evolves continually. Each discovery illuminates previously hidden areas, revealing new mysteries even as old ones are solved. After the Higgs discovery, the scientific gaze turned toward precision, measuring exactly how it decays into photons, W bosons, or various quarks, searching for minute anomalies that could indicate new physics lurking beyond current detection. Even minor deviations could hint at higher-order effects from undiscovered particles, but thus far the Higgs has performed as expected, obedient to the theory. Meanwhile, the LHC itself has undergone upgrades, colliding particles at unprecedented energies and luminosities, generating more data for scrutiny and leaving open the possibility that surprises may still emerge from the quantum shadows. The search for missing pieces is not confined to particle colliders. Experiments probing dark matter, studying the subtle oscillations of neutrinos, and examining fundamental symmetries in atomic transitions all contribute to the same quest, uncovering what the Standard Model cannot explain. The Higgs discovery demonstrates the power of human ingenuity to detect absence, to hypothesize what must exist, and to design experiments capable of revealing it. Yet the next missing piece could be far more elusive, perhaps interacting so weakly or manifesting at energies so extreme that current technology cannot yet probe it. The discovery also shapes the social and economic fabric of science. Projects like the LHC require billions of dollars and decades of collaborative effort, and funding is often justified by the promise of uncovering such crucial missing elements. Even after the Higgs was found, curiosity and the unresolved mysteries of physics continue to drive proposals for ever more ambitious colliders capable of probing higher energies or measuring the Higgs with extraordinary precision. Some scientists advocate for new types of accelerators, intense beam facilities, or even sophisticated cosmic ray experiments to glimpse phenomena beyond reach today. In a philosophical sense, the tale of the Higgs underscores the power and rigor of the scientific method. Theories are not idle conjectures. They are predictive frameworks, and when the predictions are confirmed, when a particle anticipated by equations is indeed observed, it validates the theoretical structure. The Standard Model, already a triumph, gained new prestige with the Higgs discovery, but this does not imply a final, unassailable truth about the universe. The unsolved aspects remain. The puzzle now includes the dark matter that permeates galaxies, the energy that accelerates cosmic expansion, and the enigmatic forces of gravity at quantum scales. Solving these may require particles, fields, or concepts that transcend the current paradigm. The Higgs story reminds us that science is iterative, that every revelation can expand the frontier of the unknown. While the Standard Model is complete in its particle roster, it is incomplete as a universal theory. The search for missing pieces now shifts to dark matter, the unification of quantum mechanics with general relativity, and other cosmic enigmas. The Higgs boson stands as a testament to humanity's ability to reach into the fabric of nature, uncover what was predicted yet unseen, and then confront the deeper mysteries that remain, extending the horizon of inquiry and imagination ever further. Sometimes people worry that uncovering a missing piece in physics might signal an endpoint, as if the universe had whispered all its secrets and left scientists with nothing new to explore. Yet history tells a different story. The discovery of the Higgs boson, far from closing a chapter, ignited an entirely new series of questions and avenues for research. Scientists began probing the particle's stability, contemplating whether variations of the same underlying mechanism might exist, exploring the possibility of additional scalar fields, and investigating how this discovery might weave into the fabric of even larger cosmic mysteries. The narrative of a missing piece is never a simple checkmark on a list. Each solution widens the lens of inquiry, revealing unexpected complexities and offering fresh angles from which to view the universe. For those who have traced the story from its earliest theoretical murmurs in the 1960s to the triumphant experimental confirmation in 2012, there is a dual sense of closure and anticipation. The particle once missing is now found. The Standard Model stands reinforced, and yet physics continues its relentless pursuit of the unknown. The Higgs discovery is a landmark, but not a final destination on humanity's quest to understand the universe at its most fundamental level. It exemplifies the extraordinary power of collaboration, advanced technology, and imaginative theoretical insight, and it sets the stage for the surprises yet to come. Peter Higgs, the man whose name would become synonymous with this breakthrough, did not fit the stereotypical image of a revolutionary physicist. Born in Newcastle upon Tyne in England in 1929, he displayed an early talent for mathematics and a quiet, determined curiosity about the universe. He navigated the disruptions of wartime and personal challenges, yet throughout he nurtured a deep fascination with the underlying order of nature. In the 1960s, as particle physics was emerging as a formal discipline, Higgs proposed an idea that seemed audacious: the existence of a field that could endow fundamental particles with mass. On paper, it offered an elegant solution to one of the most persistent problems in the Standard Model. Yet, many met the idea with skepticism, in part because Higgs was unassuming, reserved, and not prone to flamboyant proclamations. His style allowed the ideas themselves to carry the weight. Higgs's path to this concept was gradual. a mosaic of insights rather than a single moment of revelation. He followed the mathematics of symmetry and gauge theories, paying close attention to the phenomenon of spontaneous symmetry breaking, which originated in condensed matter physics and described how symmetries in nature could be disrupted under certain conditions. By drawing parallels between these ideas and the world of subatomic particles, he began to glimpse a solution to a long-standing puzzle: why some particles have mass while others, like photons, remain massless. The standard model at the time was incomplete. Protons, neutrons, and electrons were no longer sufficient to describe the growing zoo of fundamental particles discovered through cosmic ray observations and early accelerator experiments. Quantum field theory offered the language, but calculations predicted nonsensical infinities unless particles like the W and Z bosons were assumed massless, contradicting experimental evidence. Higgs and his contemporaries were determined to solve this contradiction. Higgs's temperament proved essential. He faced criticism with patience, letting his rigorously constructed mathematical papers speak for themselves. These works proposed that a background field pervading space could give particles their mass through interaction. The idea was extraordinary: a universal field spontaneously breaking symmetry, producing detectable effects. More astonishing was the implication that this field would have a quantum excitation. A particle, the Higgs boson, with spin zero and properties entirely unlike any other known particle. Detecting it required energy scales far beyond the technology of the 1960s, leading many to dismiss the concept as untestable. Meanwhile, the theoretical landscape was crowded with competition and collaboration. Other scientists from Belgium, the United States, and Japan were independently exploring spontaneous symmetry breaking. Yet, Higgs's name became attached to the particle because he explicitly predicted a massive scalar boson. His papers were initially rejected by journals, yet his persistence, meticulous reasoning, and calm demeanor allowed the idea to endure. Though he appeared disconnected from the theatricality of academic life, Higgs understood the stakes. A mass-giving field could complete the framework uniting electromagnetism and the weak nuclear force. By the late 1960s and early 1970s, the idea gained traction. The mathematics demonstrated remarkable coherence, and theoretical resistance began to wane, though experimental confirmation remained distant. References to the Higgs field and mechanism appeared increasingly in theoretical papers, eventually becoming a cornerstone of the Standard Model, which elegantly unified the electromagnetic, weak, and strong forces. Some mysteries remained, notably gravity, but the mass problem no longer seemed insurmountable. Higgs himself maintained a modest career, teaching at institutions such as the University of Edinburgh. For decades, the Higgs field was largely theoretical, a background fixture in particle physics awaiting experimental validation. As accelerator technology advanced, scientists designed machines capable of reaching the necessary energy scales. In the late 1980s and early 1990s, ambitious projects like the superconducting super collider in the United States were proposed to pursue the Higgs, though the project was ultimately canceled, leaving the particle elusive. Even in its absence, the Higgs boson inspired generations of physicists, bridging theoretical elegance with the promise of empirical discovery. It remained a beacon, guiding experimentalists and theorists alike toward a deeper understanding of the universe. The pursuit of this particle exemplified the painstaking interplay of imagination, collaboration, and technological innovation, illustrating that in physics, no solution ends the journey. Every answer opens new questions, and every discovery is both a milestone and a gateway. The narrative of the Higgs boson, from theoretical conjecture to experimental triumph, is not merely a tale of one particle, but a testament to human curiosity and perseverance. It reflects how ideas, nurtured quietly and patiently, can eventually transform the way we comprehend the cosmos. Each layer of understanding reveals new mysteries, ensuring that the story of physics remains dynamic, ever-expanding, and infinitely compelling. Then the Large Electron-Positron Collider LEP at CERN in Switzerland began to probe energy scales that increasingly constrained the possible range of masses for the Higgs boson. The collider pushed the boundaries of human knowledge, smashing particles together at energies never before achieved, each collision sending ripples of possibility through the physics community. Even with these advances, however, it was still not sufficient to detect the elusive particle conclusively. Peter Higgs, the man whose theoretical insight had predicted its existence, observed these developments quietly from the sidelines. He visited research centers on occasion, delivering talks to share his perspective, yet he never cultivated a charismatic public persona or sought the spotlight. Throughout this period, his core conviction remained steady. If the standard model of particle physics was correct, and if his concept of spontaneous symmetry breaking accurately described nature, then the boson should appear at sufficiently high energies. Yet he never lost sight of the uncertainty inherent in his assumptions. He knew that nature might have surprises in store, that the mechanism responsible for giving particles mass could be far more intricate than his elegant model suggested. This lingering doubt was a constant companion. Some in the field speculated that multiple Higgs bosons could exist, that the underlying field might be vastly more complex, or that entirely different phenomena might replace the mechanism he envisioned. But despite these unknowns, the elegance of his theory, coupled with the early experimental hints emerging from successive colliders, fueled growing optimism among physicists that the Higgs boson would eventually be observed. Higgs never patented his idea or guarded it as proprietary knowledge. Instead, it was freely integrated into the collective framework of theoretical physics, becoming a foundational concept almost by consensus. By the start of the 21st century, a new generation of physicists and engineers at CERN was preparing the launch of the Large Hadron Collider, the LHC. Towering over its predecessors in both scale and energy capacity, it was the first machine capable of definitively detecting the Higgs boson within the predicted mass range. For Peter Higgs, now older and retired from active teaching, the LHC represented the culmination of decades of theoretical speculation and careful, methodical calculation. As the LHC came online, torrents of data began to flow, and the eyes of the world turned toward this unprecedented scientific quest. Suddenly, Peter Higgs found himself at the center of a whirlwind of attention, a position he was notoriously uncomfortable with. Physicists everywhere were eager to see if the collision data would confirm the Higgs boson's existence or reveal something even stranger, and the stakes were high. If the Higgs failed to appear within the LHC's energy reach, the entire standard model could face serious challenges. As preliminary results and leaks began to circulate, indications emerged pointing to a particle with a mass of roughly 125 giga-electronvolts, comfortably within the expected range. On July 4, 2012, CERN officially announced the discovery of a new particle matching the predicted properties of the Higgs boson. The announcement was a moment of triumph and relief, particularly for the experimental teams whose painstaking work had made the detection possible. Yet, the name Higgs echoed far beyond the walls of laboratories, reaching even the general public. Peter Higgs accepted the accolades with a mixture of gratitude and mild discomfort, repeatedly emphasizing that he was just one part of a much larger scientific endeavor. He acknowledged the contributions of contemporaries such as Francois Englert, Robert Brute, Gerald Guralnick, C.R. Hagen, and Tom Kibble, who had independently arrived at similar theoretical insights. Nevertheless, the connection between his name and the boson was indelible. It was his bold conceptual leap that had, after nearly 50 years, been confirmed in the laboratory. His story exemplifies a quieter, but no less profound style of scientific pursuit. Unlike some figures who command public attention with dramatic pronouncements, Higgs worked methodically behind the scenes, developing arguments with precision and allowing the mathematical rigor of his work to speak for itself. The eventual payoff was monumental, yet it relied on a generation of technological advances catching up to theoretical foresight. In retrospect, the existence of such a field might seem inevitable, but in the early 1960s, the idea was a daring intellectual leap, rooted in abstract mathematics and difficult for many to take seriously. Over the following decades, the Standard Model evolved around this concept, incorporating the Higgs mechanism into a cohesive framework explaining how the fundamental forces except gravity govern the universe. Higgs remained modest and somewhat uncomfortable with fame, publicly resisting the nickname God particle that popular media attached to the boson. He maintained an awareness of the collaborative nature of scientific progress, emphasizing the joint efforts of many theorists who contributed to the theoretical breakthroughs. Following the discovery, he received numerous awards and honors, including the Nobel Prize in Physics, which he shared with Francois Englert in 2013. This recognition confirmed the enormous impact of what had begun as a speculative paper decades earlier. The radical aspect of the idea was less in the mathematics, which drew on pre-existing concepts of spontaneous symmetry breaking, and more in the notion that such a particle could be experimentally verified. Confirming the Higgs required overcoming enormous technological hurdles, exemplified by the LHC, a 27-kilometer circumference accelerator that remains one of the most complex instruments ever built. The journey highlights a fundamental truth about science. Theory and experiment often evolve on different timescales, requiring decades of iterative development before alignment occurs. Higgs's theoretical mechanism demanded precise experiments to confirm its predictions, and only with the gradual improvement of accelerators, data analysis techniques, and global collaboration did experimental verification become possible. For him, the discovery was both the culmination of a lifetime's work and a humbling reminder of the vast scale of human scientific endeavor. The essence of the Higgs mechanism can be understood without heavy jargon. Empty space is not truly empty. It is filled with a pervasive Higgs field. This field interacts with certain fundamental particles, imparting mass while leaving others unaffected. The mathematics of gauge symmetry dictates that if such a field exists, it must be accompanied by a boson, now known as the Higgs boson. Higgs carefully derived these results, presenting them methodically and allowing the logic of the theory to carry the argument. Over time, this idea became a cornerstone of the Standard Model, guiding how physicists interpret data from particle collisions and cosmic observations. Higgs's journey was far from straightforward. It involved repeated journal rejections, skepticism from colleagues, and the ever-present risk that nature might defy theoretical expectations. Yet, step by step, as gauge symmetries in the electroweak interaction were understood and increasingly powerful colliders were built, the pieces finally fell into place. Today, his name is inseparable from one of the most important discoveries in particle physics. His quiet demeanor serves as a reminder that transformative science does not require flamboyance. Sometimes a clear, mathematically grounded idea and the patience to see it realized are enough. What once seemed a bizarre notion, a universal field giving mass to particles, became a foundational element of our understanding of reality. Higgs may never have anticipated the scale of public attention his discovery would attract. Given his reluctance toward publicity, it is likely he did not. Yet his legacy is forever entwined with the boson that bears his name, a particle that has fundamentally reshaped our understanding of the universe. He may have been a reluctant figurehead, but his contribution exemplifies the power of insight applied to theoretical gaps, transforming speculative ideas into verified scientific truth. The story of Higgs and his theoretical breakthrough also illustrates a broader lesson about science. Major advances often emerge in quiet offices and handwritten notebooks long before they capture headlines. Ideas take root when they resonate with existing knowledge and remain testable even if verification is decades away. In Higgs's case, the triumph was witnessing this process complete within his lifetime, culminating in a discovery that altered the landscape of physics forever. The Higgs mechanism, in essence, explains how particles acquire mass. Empty space is not void. It is suffused with the Higgs field, which interacts with certain particles to give them mass while leaving others unaffected. Fields are fundamental constructs in physics. The electromagnetic field governs light and magnetism, and similarly, the Higgs field underpins the mass of fundamental particles, silently shaping the universe from behind the scenes. The Higgs field, however, stands apart in the vast landscape of physics because it possesses a value that is constant everywhere in the universe, and certain particles have a unique way of interacting with it. To grasp the fundamentals, picture the universe as permeated by an invisible medium through which all particles must move. Particles that interact strongly with this medium appear sluggish and heavy, while those that barely interact glide effortlessly, effectively behaving as if they have no mass at all. This image is metaphorical, yet it captures the essence of how the Higgs field functions. The field is omnipresent, and the extent to which a particle couples to it directly determines that particle's mass. In the quantum world, every field can be excited in discrete, indivisible amounts called quanta. For the electromagnetic field, the quantum is the photon. For the Higgs field, the quantum is the Higgs boson. This means that disturbances in the Higgs field can manifest as tangible particles that experimental physicists can detect. The discovery of the Higgs boson was the critical evidence confirming that the Higgs field is not just theoretical, it is real and operational within our universe. The term mechanism in this context refers to spontaneous symmetry breaking, a concept that lies at the heart of modern particle physics. Symmetry is a fundamental principle in physics. A system is symmetric if it looks the same when rotated, flipped, or shifted in time. Gauge symmetries, in particular, dictate how particles and forces interact. If these symmetries were perfect, particles such as the W and Z bosons, which mediate the weak nuclear force, would have no mass. Yet experiments unmistakably show that these bosons do have mass. Symmetry breaking provides the solution. A common analogy is a pencil balanced on its tip, perfectly symmetrical in theory, yet the slightest disturbance causes it to topple in a specific direction, breaking that symmetry. In the Higgs field, the lowest energy state is not as symmetric as the underlying equations might suggest. The field settles into a particular value across all of space, altering the interactions of certain particles with it. This controlled symmetry breaking allows the W and Z bosons to gain mass due to their strong coupling with the Higgs field, while the photon, which does not interact with the field, remains massless. This difference is crucial, providing a framework to unify electromagnetism and the weak nuclear force into a single electroweak theory. At low energies, the symmetry appears broken, but at a deeper level, it remains fundamentally unified. For the Higgs mechanism to hold mathematically, quantum field theory had to accommodate the complexities of spontaneous symmetry breaking. When first proposed in the 1960s, this was far from trivial. A major achievement was proving that the theory remained renormalizable even after symmetry breaking, meaning calculations did not spiral into uncontrollable infinities. This proof convinced many skeptical physicists that the Higgs mechanism was more than a clever idea, it was a rigorous, workable theory. The Higgs field does not account for all mass in the universe. Photons remain massless, and neutrinos, once thought massless, acquire only a small mass that the Higgs mechanism does not fully explain. Most of the mass of protons and neutrons arises from the strong nuclear force binding quarks together, though the Higgs field is essential for giving quarks their tiny intrinsic masses, which are then amplified by strong force interactions. Without the Higgs mechanism, atoms could not exist as we know them. Chemical reactions would be fundamentally altered, and biological life, dependent on stable, massive particles, might never have emerged. Experimentally, proving the Higgs mechanism required the direct detection of the Higgs boson. For decades, physicists relied on indirect evidence, studying the behavior of the W and Z bosons and deducing that some field must be responsible for their mass. Direct observation was essential. The 2012 discovery at the Large Hadron Collider, with the Higgs boson appearing at around 100-125 giga-electron volts, matched theoretical predictions and confirmed the field's existence. Although the mechanism is mathematically sophisticated, involving concepts such as group theory and gauge invariance, its practical essence is simple. The Higgs field pervades the universe, spontaneously settles into a uniform state, and interacts differently with different particles. The strength of this interaction determines each particle's mass. The story of mass, however, does not end with the Higgs field. Mysteries remain, including the nature of dark matter, which might consist of particles that do not interact with the Higgs field, explaining their elusiveness, and the origin of gravity, which the Higgs mechanism does not address. The Higgs field provides the backbone for much of the visible universe, but the cosmos still holds secrets beyond its reach. Moreover, some scientists speculate that the universe might not be limited to a single type of Higgs boson. There is the possibility that the Higgs we have discovered is only one part of a more intricate framework, perhaps embedded within concepts like supersymmetry or hidden extra dimensions. Yet, despite these tantalizing possibilities, the central premise remains steadfast within the standard model of particle physics as we understand it today. The Higgs field is not merely a mathematical abstraction, it is a pillar of our comprehension of the universe. It exemplifies the extraordinary reach of theoretical physics. The human mind conceived a strange, invisible field capable of breaking symmetry and generating an entirely new type of particle, and decades later, experimental evidence confirmed its existence. This journey from hypothesis to discovery demonstrates how nature can appear deceptively simple while simultaneously harboring profound mysteries. The emergence of mass from a pervasive, universal field is elegant in its simplicity, yet it sparks deeper questions. Why does the Higgs field have the specific value it does? Why does it interact differently with distinct particles, bestowing mass in such precise ways? Much of the ongoing research focuses on refining our measurements of the Higgs boson itself. By observing its decay patterns into other particles, recording the frequency of its appearance in high-energy collisions, and seeking any unexpected characteristics, physicists aim to uncover hints of physics beyond the standard model. Thus far, the Higgs boson has behaved largely in line with theoretical predictions, but researchers remain vigilant, knowing that any anomaly could reveal a layer of reality previously unimagined. In popular culture, the Higgs mechanism is sometimes romanticized as a mystical source of mass, yet its true significance is grounded in the complex web of quantum field interactions. Mass is not a single unified property. It emerges from multiple mechanisms and forces interacting within the universe. The Higgs field operates at a fundamental level, providing elementary particles with baseline masses without which the structure of the standard model would collapse. Its role is essential in maintaining the coherence of the universe at its most basic level. The discovery and experimental verification of the Higgs mechanism represent a crowning achievement of 20th century physics, brought into full clarity in the 21st century through painstaking observation and experimentation. It reconciled long-standing theoretical contradictions, unified aspects of the electroweak theory, and opened the door to profound questions about the very fabric of reality. It is a testament to how an abstract theoretical insight arising from the study of symmetry and its breaking can evolve into a foundational element of our understanding of the universe. Although Peter Higgs is the name most commonly associated with the mass-generating mechanism, he was far from alone in this intellectual achievement. During the early 1960s, multiple brilliant theorists explored the same core ideas: spontaneous symmetry breaking, gauge invariance, and how particles could acquire mass without undermining the intricate mathematics of quantum field theory. Francois Englert and Robert Brood in Belgium, alongside Gerald Guralnick, C.R. Hagen, and Tom Kibble in the United States and Britain, were developing parallel frameworks. Their work often coincided with Higgs's research, sometimes appearing in publication within weeks of his own papers. Englert and Brout, working at the Free University of Brussels, investigated how a scalar field could spontaneously break symmetry within a gauge theory. Their August 1964 paper introduced concepts remarkably similar to Higgs's later proposals. Though often overlooked in popular narratives, their contributions laid critical groundwork. Their approach described how a massless scalar field could acquire a non-zero vacuum expectation value, thereby endowing gauge bosons with mass. They did not, however, explicitly identify the scalar boson as a new particle, though they hinted at its potential existence. Meanwhile, Peter Higgs experienced initial rejection of his first short paper. In its revision, he added a decisive paragraph explicitly identifying the massive boson that would emerge from the field he proposed. This explicit mention of the particle cemented his association with the discovery in public consciousness. The earlier papers by Englert and Brout implied the boson, but Higgs's clear articulation provided a distinct edge in recognition. Around the same time, Guralnick, Hagen, and Kibble were independently pursuing the same theoretical trail. Their October 1964 paper in Physical Review Letters offered another formulation, demonstrating that gauge bosons could gain mass in a spontaneously broken symmetry scenario without violating the principles of quantum field theory. Their rigorous mathematical treatment clarified the mechanism's necessity and sufficiency. Collectively, these six theorists, Englert, Brout, Higgs, Guralnick, Hagen, and Kibble, are often referred to as the architects of the Higgs mechanism. Depending on the level of inclusivity, the mechanism has been variously named the Brout-Englert-Higgs mechanism, the BEH mechanism, or even the Englert-Brout-Higgs-Guralnick-Hagen-Kibble mechanism. Over time, popular accounts typically simplify the term to the Higgs mechanism or the Higgs field, though this has occasionally sparked debate, given the near-simultaneous contributions of multiple researchers. Robert Brout passed away before the Nobel Prize was awarded in 2013, leaving a gap in recognition felt by the community, as his contributions paralleled those of Englert. Nevertheless, Englert shared the prize with Higgs, while Guralnick, Hagen, and Kibble did not, expressing a mix of pride and disappointment. The Nobel Prize rules, which allow a maximum of 3 living recipients, made it impossible to honor all contributors equally. Despite this, historical accounts consistently acknowledge the roles of all 6 theorists who received numerous other awards and accolades over time. The fertile intellectual environment in which these researchers operated drew heavily on condensed matter physics. In superconductivity, for instance, particles appear to gain mass through interactions with a condensate, a concept adapted to particle physics by these theorists. They recognized that vacuum states could possess non-trivial structure rather than being empty, and understood that a scalar field acquiring a vacuum expectation value could provide mass to gauge bosons without disrupting gauge invariance. Higgs independently arrived at a similar conclusion and further emphasized the physical existence of the scalar boson as an unavoidable byproduct. Guralnick, Hagen, and Kibble expanded these ideas, showing that the mechanism functioned under general conditions, thus shaping the Standard Model in profound ways. Prior to these developments, unifying electromagnetism and the weak force was nearly impossible without conflicting with the observed masses of the W and Z bosons. Following these insights, the emerging electroweak theory, largely formalized by Steven Weinberg, Abdus Salam, and Sheldon Glashow, incorporated the Brout-Englert-Higgs-Guralnick-Hagen-Kibble mechanism as a central element. This framework laid the foundation for the modern Standard Model, one of the most robust and predictive structures in physics today. Interactions among these theorists were not always harmonious, as academic credit and priority can be sensitive topics. Some were aware of each other's progress in real time, while others only discovered it through published papers. Despite initial tensions, mutual respect grew over time. Higgs, in particular, often corrected journalists who attributed sole credit to him, emphasizing the contributions of Englert, Brout, Guralnick, Hagen, and Kibble. This collaborative recognition illustrates a hallmark of scientific progress, multiple minds advancing knowledge simultaneously at the frontier of discovery. Beyond these 6, other physicists laid foundational insights. Julian Schwinger, Yoichiro Nambu, and others explored spontaneous symmetry breaking in various contexts, influencing the younger generation to apply these concepts to particle gauge fields. Their indirect contributions were pivotal in shaping the theoretical landscape. Over decades, theorists refined the Higgs mechanism, addressing questions about detectability, mass predictions, and possible variants predicting multiple Higgs bosons. Each new experimental result from accelerators prompted updates to the theory, ensuring consistency with empirical data while extending the boundaries of human understanding. However, the central concept that gauge bosons could acquire mass through spontaneous symmetry breaking in a scalar field persisted, unwavering, through decades of theoretical debate. By the time construction of the Large Hadron Collider began, this mechanism had achieved near-universal acceptance among particle physicists. The boson itself remained elusive. Yet, the remarkable success in predicting the properties of the W and Z bosons, coupled with the precision of electroweak measurements from earlier colliders, provided compelling indirect evidence that the Higgs field was indeed real. The only element missing was a direct observation, a moment of experimental confirmation that would definitively seal the theory. That moment arrived in 2012. Peter Higgs was alive to share in the Nobel Prize recognition, but Francois Englert, who had independently contributed, was also honored, while Robert Brout, Gerald Guralnick, and Tom Kibble had passed away, and thus were excluded by the Nobel Committee's limitations. In public statements, Guralnik and Kibble extended their congratulations to Higgs and Englert, acknowledging both the constraints of the prize and the timing of events. Had the experimental discovery occurred decades earlier, more of the original contributors might have shared the accolade. The delayed confirmation of theory by experiment illustrates a peculiar truth in the history of science. Recognition often depends not only on intellectual achievement, but also on timing, mortality, and the subjective interpretation of committees. Even beyond awards, the scientific community continues to honor Guralnik, Hagen, and Kibble as essential figures in the development of the mechanism. The Higgs story exemplifies that groundbreaking science rarely emerges from solitary genius. Even the most visionary thinkers depend on contemporaries who test, extend, and occasionally validate ideas by pursuing parallel inquiries. The emergence of the Higgs mechanism showcases how multiple groups, working independently yet within the same conceptual landscape, converged on a similar solution once the theoretical framework was mature enough. This convergence enhances the robustness of discovery. It is rarely a single eureka moment of an individual mind. Rather, it is the intersection of multiple insights, each filling a critical gap in the collective understanding. In this case, Englert and Brout demonstrated that a spontaneously broken scalar field could endow gauge bosons with mass. Higgs proposed the existence of a new particle intrinsically linked to this field. Guralnik, Hagen, and Kibble provided a generalized proof and rigorous analysis that explained why the mechanism operated consistently within a gauge theory. Collectively, these contributions laid the foundation for what became one of the pillars of the Standard Model. The process highlights the intricate beauty of collaborative science. The exchange of ideas, the subtle distinctions in approach among different papers, and the overlapping efforts all contributed to a richer, more resilient theoretical structure. These physicists did not simply solve a pressing theoretical puzzle about particle mass. They opened the door to an entirely new realm of particle physics. Their framework anticipated experimental phenomena and ultimately predicted one of the most exciting particle discoveries of the modern era. Today, students learn about the Brout-Englert-Higgs-Guralnik-Hagen-Kibble mechanism, even though popular accounts often reduce it to the Higgs mechanism. Textbooks present the refined, polished version, but the historical record reveals a messy, overlapping process involving multiple thinkers. The journey from the seminal papers of 1964 to the eventual experimental confirmation nearly 50 years later illustrates both the patience required in science and the extraordinary scale of resources needed to validate such a fundamental theory. While Higgs remains the most widely recognized name publicly, closer examination underscores the indispensable roles of his contemporaries. Without Guralnik, Hagen, and Kibble, the theoretical underpinnings of the Higgs field would have been incomplete and less convincing. Without them, the Standard Model might not possess its current robustness. Their collective achievement serves as a reminder that scientific breakthroughs flourish not in isolation, but within a dynamic interplay of minds striving toward a shared understanding of reality. Scientific progress always balances revelation with skepticism. Even revolutionary ideas face initial caution, and the Higgs boson was no exception. When the mechanism explaining particle mass first emerged, it was not immediately embraced. Some physicists worried the proposal was too convenient, too ad hoc, or inherently untestable. The notion of a new particle with an associated field seemed provisional rather than fundamentally transformative. Questions arose regarding whether the mathematics adequately captured deeper truths or merely patched existing theories. The Standard Model already struggled to account for phenomena like gravity, dark matter, and other unresolved mysteries, leaving room for doubt. Skepticism compelled careful scrutiny, ensuring that alternatives were considered and predictions rigorously tested. During the 1960s, competing mechanisms for mass generation appeared, though none attracted the same attention as the Higgs proposal. Some involved more complex fields or were embedded in ambitious unified theories, attempting to solve multiple puzzles simultaneously. A prevailing concern was that any explanation for particle mass had to relate to broader phenomena, such as multiple symmetry-breaking phases in the universe. Critics questioned whether attributing mass to a single field oversimplified a potentially multifaceted reality. Practical concerns compounded theoretical caution. Detecting the Higgs boson required energy scales far beyond what existing colliders could achieve. The particle was predicted to be relatively massive, making its creation in high-energy collisions an expensive, technically demanding endeavor. History had already demonstrated that promising theories often languished for decades awaiting experimental confirmation, and many feared the Higgs might share that fate. Through the 1970s and 1980s, the Standard Model flourished. New quarks were discovered, the W and Z bosons were observed at CERN's superproton synchrotron, and the theory proved resilient under experimental testing. Ironically, these successes intensified skepticism toward the Higgs boson. In physics, a single missing element may seem negligible if the rest of the framework functions accurately. Some theorists questioned whether the absence of a direct observation indicated a fundamental gap or merely an isolated anomaly. Concurrently, alternative frameworks like supersymmetry promised to unify unresolved questions in particle physics, suggesting that mass generation could follow a different or complementary path. Funding concerns further fueled debate. Constructing next-generation colliders demanded billions in investment, and policymakers scrutinized whether pursuing an elusive particle justified the cost. Critics argued that resources devoted to the Higgs could detract from more immediate or potentially transformative research. Skepticism also arose from the theoretical nature of scalar fields themselves. Scalar fields, unlike gauge fields, are relatively rare and lack certain symmetries that simplify predictions for force carriers. The hypothetical Higgs field raised concerns about vacuum stability, theoretical consistency, and the hierarchy problem, the puzzling disparity between the electroweak scale and gravity. The Higgs boson's relatively low mass implied an improbable fine-tuning, prompting questions about whether the theory was truly complete or if new physics awaited discovery. This uncertainty was not merely academic. By the late 1980s, when CERN's Large Electron Positron Collider began probing Higgs candidates within a limited energy range, repeated non-detections only sharpened doubts. Each negative result narrowed the possible mass window without delivering definitive confirmation, reinforcing the need for ever more powerful experimental facilities. In the 1990s and early 2000s, critics focused less on denying the Higgs boson's existence and more on the escalating complexity and cost of the machines needed for its discovery. Plans for the superconducting supercollider in the United States exemplified these challenges, as it promised even greater energy capabilities than the Large Hadron Collider would eventually achieve. The scientific, financial, and technical hurdles surrounding the Higgs boson underscore both the ambition and the collaborative spirit inherent in modern particle physics, highlighting a half-century-long journey of theory, doubt, and eventual triumph. The Superconducting Supercollider, or SSC, however, met its abrupt end in 1993, the victim of both financial constraints and the shifting tides of political will. Funding concerns loomed large, but politics, with its relentless and often unpredictable currents, played an equally decisive role. When the cancellation was announced, those who had long questioned the wisdom of such monumental scientific undertakings celebrated. For them, it was a triumph of caution over ambition. They argued that the scientific community needed to respect practical limits, to balance curiosity with feasibility. The Higgs boson, they claimed, might hold profound theoretical significance, but its pursuit did not justify the expenditure of billions. This episode cemented a broader perception. Chasing the Higgs was a venture fraught with risk, with no guarantee that any collider, however vast or sophisticated, would reveal the elusive particle. Yet, amid the skepticism, small but determined groups of physicists pressed on. They refined theories, dissected calculations, and scoured accelerator data from around the globe. Patterns began to emerge. Certain particle decay processes hinted at the Higgs' invisible hand, aligning with the predictions of a Higgs-infused standard model. Slowly, the arguments from critics narrowed. Could there be not one Higgs boson, but an entire family of related particles? Was the simplest version of the Higgs mechanism truly the right one, or would nature unveil something entirely unexpected just beyond the horizon? The tension between the Standard Model's triumphs and its glaring gaps became the focal point of the debate. The model worked extraordinarily well, yet it left profound questions unanswered, forcing some to doubt whether a single field could genuinely account for mass without addressing the universe's other mysteries. As the Large Hadron Collider, or LHC, approached its first proton beams in 2008, this atmosphere of skepticism remained palpable. Scientists faced the dual task of convincing both policymakers and the public that exploring the Higgs was worthwhile, even if it meant building the largest and most intricate machine humanity had ever attempted. Skeptics pointed to the immense costs and the careers devoted to a particle that might never materialize. Believers countered by invoking history. Ambitious experiments had previously succeeded, from discovering the W and Z bosons to confirming intricate predictions of quantum electrodynamics. They insisted that science, by its very nature, demanded risk. The potential payoff, the chance to understand why matter possesses mass, was worth the gamble. When the LHC began operating, a wave of anticipation swept through the physics community. Early data offered tantalizing hints, but caution prevailed. Researchers were acutely aware of the scientific culture shaped by prior false starts and premature announcements. Small signals appeared sporadically, but no one dared declare discovery without rigorous confirmation. As data accumulated, skepticism evolved into careful observation. Initial spikes in collision data prompted debate. Were they genuine indications of the Higgs or statistical anomalies? Even the most ardent believers acknowledged that the particle might not perfectly match the Standard Model's predictions. In 2012, CERN announced the observation of a new particle consistent with the Higgs boson. Some skeptics conceded that a milestone had been reached, while others reframed the debate, suggesting that this might be an exotic version, not the textbook Higgs. The real test, they argued, lay ahead. Precise measurements of the particle's properties, decay channels, and interactions would determine whether it conformed to the Standard Model or hinted at new physics. Even after confirmation, skepticism persisted, shifting toward deeper questions: the Higgs' role in cosmic inflation, its potential connection to dark matter, and issues of fine-tuning in the universe. These discussions illustrated that skepticism does not vanish in the face of discovery. It transforms, guiding science toward ever more nuanced inquiry. The opposition to the Higgs concept, far from obstructing progress, played a constructive role. It forced physicists to articulate the rationale behind their beliefs and to define experimental pathways for verification. It inspired alternative models, some of which remain relevant should future data reveal anomalies. Skeptics, often cast as antagonists, provided balance, ensuring ideas were rigorously tested. Their insistence on caution influenced the LHC's design, prioritizing precision measurements over simple binary detection. Today, the Higgs boson is a confirmed element of the Standard Model, yet unanswered questions persist. The nature of dark matter, the origins of neutrino mass, and whether the Higgs is part of a larger spectrum of scalar particles. Early doubts about a single field accounting for mass still carry weight, underscoring how much remains mysterious. The journey from skepticism to discovery exemplifies the scientific process. Ideas are proposed, questioned, refined, and ultimately tested with the most sophisticated tools available. Even validated theories remain subject to scrutiny as new evidence emerges. The pushback against the Higgs has not ended. It has merely entered a new phase, probing deeper into the universe's secrets and demonstrating that each discovery often raises even greater mysteries. The LHC itself did not materialize overnight. It was born from decades of research, engineering, negotiation, and global collaboration. Early particle accelerators were smaller, confirming aspects of the Standard Model, but as ambitions grew, so did the machines. Scientists realized that probing higher energies required a collider of unprecedented scale. The LHC was conceived to smash protons together at energies never before achieved in a laboratory, theoretically producing the Higgs and potentially other unknown particles. Designing the LHC involved solving immense technical challenges. Engineers had to plan collision types, devise detectors capable of capturing the resulting particle debris, and manage the colossal volumes of data generated. High-energy collisions produce cascades of particles whose energy, momentum, and properties must be meticulously traced. Traditional computing systems could not handle the data, prompting the development of grid computing. By distributing processing across thousands of machines worldwide, scientists could sift through billions of collisions in search of rare Higgs-like events. Reaching the required energies demanded superconducting magnets to steer and focus the proton beams around the 27-kilometer circular tunnel beneath the Swiss-French border near Geneva. These magnets operate mere degrees above absolute zero, maintained by one of the planet's largest cryogenic systems using liquid helium. Materials science and engineering were pushed to the limits to ensure the magnets could carry the necessary currents without losing superconductivity. Any quench, a sudden loss of superconductivity, would require powering down sections for repairs. The LHC repurposed the existing tunnel from the Large Electron Positron Collider, stripping out old infrastructure and installing new systems optimized for protons. Protons, heavier than electrons, can reach higher energies without excessive radiation losses, but their composite nature complicates collision analysis. Despite this, they offered a viable path to producing the heavy, rare particles scientists sought. Financing the project was monumental, requiring international cooperation, political negotiation, and a commitment to a vision of discovery that spanned decades. Every component, from the magnets to the computing grids, reflected decades of incremental progress, cumulative knowledge, and persistent human curiosity. The LHC was not merely a machine. It was a testament to what humanity can achieve when ambition, ingenuity, and patience converge, all in pursuit of answers to questions that had haunted physicists for generations. CERN, the European Organization for Nuclear Research, relied on contributions from multiple member states, each navigating its own budget limitations and political pressures. Beyond these core contributors, partnerships with non-member nations played an essential role, bridging gaps and strengthening the collective effort. Securing funding was a continuous negotiation, a balancing act of national priorities and scientific ambition. Some saw the Large Hadron Collider as the crown jewel of European scientific collaboration, a symbol of progress and curiosity at a continental scale. Others regarded it as a costly luxury, especially during times of fiscal restraint. Yet the allure of unraveling the mysteries of particle physics proved persuasive, keeping support alive. Over time, as the LHC's promise for groundbreaking discoveries became evident, an increasing number of countries joined, either as full CERN members or through specialized agreements, to contribute to particular detectors or research programs. The detectors themselves represent extraordinary feats of engineering. 4 major experiments, ATLAS, CMS, ALICE, and LHCb, occupy distinct points around the collider's circular tunnel, each tailored for specific aspects of particle physics. ATLAS and CMS, towering multi-story constructions, serve as general-purpose detectors capable of capturing a broad spectrum of phenomena, including the elusive Higgs boson. These instruments are composed of intricate, multi-layered systems, inner trackers that trace particle trajectories with micrometer precision, electromagnetic and hadronic calorimeters measuring energies, and muon detectors enveloping the outer layers. ALICE focuses on heavy ion collisions, replicating conditions of the early universe to glimpse its primordial state. LHCb targets particles containing B quarks, shedding light on the imbalance between matter and antimatter. Designing and assembling these detectors demanded global collaboration, with teams from dozens of countries taking responsibility for discrete components. Every piece had to be integrated flawlessly, for even the smallest misalignment could compromise the entire experiment. The technical and safety challenges were immense. Protons accelerated near the speed of light, carry enormous energy. A misaligned magnet or an accidental beam loss could wreak havoc on the equipment. Engineers devised multiple layers of beam protection, including collimators and dump lines to safely absorb or redirect stray particles. The cryogenic system, cooling the magnets with liquid helium, required meticulous control to prevent pressure surges or system-wide failures. Early in the LHC's operation, a faulty electrical connection triggered a magnet quench, causing significant damage that took months to repair. Each setback became a lesson, driving incremental improvements to ensure safe, reliable operation at record-breaking energies. The LHC's journey from concept to reality spanned decades. Initial proposals emerged in the 1980s, with formal approval from CERN's council arriving in the 1990s. Civil engineering progressed in stages, with the installation of magnets representing one of the largest logistical challenges. Crews maneuvered massive components through the underground tunnel, placed them with near micrometer accuracy, and cooled them to their operating temperatures with liquid helium. Every phase required exhaustive testing before proceeding, and while delays were inevitable, progress moved steadily, accompanied by a sense of collective excitement that humanity was building something unprecedented. Collaboration extended far beyond Europe, with universities and laboratories worldwide contributing expertise, components, and knowledge. The LHC drew attention not only for confirming the Higgs boson, but for its potential to probe deeper mysteries, supersymmetry, extra dimensions, and the particle nature of dark matter. As energy ramp-up approached, anticipation and scrutiny intensified. Some individuals even filed lawsuits, like fearing high-energy collisions might create miniature black holes or other catastrophic events. Scientists consistently explained that any such black holes would be microscopic and evaporate almost instantly, posing no danger. The controversy highlighted the LHC's cultural and scientific significance, capturing both public imagination and anxiety. Once operational, the collider entered a new phase. Commissioning the beams, testing collisions across energies, and incrementally increasing intensity became the daily focus. By 2010, data collection was fully underway. Detectors recorded collisions in real time, while massive global computing grids filtered, stored, and analyzed the information. Initially, signals of new particles were rare and statistically subtle, but as collisions accumulated, the likelihood of detecting previously unknown phenomena increased. Close coordination between machine operators, detector physicists, and data analysts optimized beam stability, detection efficiency, and computational techniques. The announcement in 2012 of a particle consistent with the Higgs boson marked a historic milestone. Yet, the LHC story did not end there. Physicists pursued upgrades to achieve higher luminosities, allowing more collisions per second and enabling more precise studies of the Higgs boson and searches for rare or unexpected processes. Each upgrade brought fresh engineering challenges, adding or replacing magnets and injector systems, refining detect technology, and ensuring the entire infrastructure could manage the increased data flow without overwhelming systems. Over time, the LHC evolved from a discovery machine into a precision instrument, capable of detecting subtle deviations from established physical laws. In an era when large-scale science faces intense scrutiny, the LHC has demonstrated the power of international collaboration. Despite technical setbacks, budget debates, and dramatic headlines, it has produced results that have reshaped our understanding of the universe. The search for the Higgs boson was the primary driver, but the collider's legacy extends far beyond a single particle. It has cultivated a generation of scientists and engineers proficient in cutting-edge technologies, from superconducting magnets to advanced computing. Their expertise has applications beyond particle physics, influencing medical imaging, computing, and other fields. To the public, the LHC may appear as an audacious gamble, yet for those involved it represents a logical, daring step in humanity's enduring quest to decipher the fundamental laws governing nature. The journey from the initial proposal to the first operational run of the Large Hadron Collider, LHC, was marked by an undeniable series of challenges and uncertainties. Whether it was the complexities of securing funding, the monumental task of engineering such an intricate machine, or the ever-present doubts about whether the scientific payoff would justify the massive investment, the project seemed at times like an audacious gamble. Yet, at its core, the LHC represented a collective vision, a belief shared by scientists, engineers, and political leaders alike, that the exploration of the subatomic world at unprecedented energy levels would lead to breakthroughs fundamental to our understanding of the universe. The risk paid off magnificently. When the Higgs boson was finally discovered in 2012, it was a triumph not just for the LHC, but for the entire scientific community. The discovery confirmed the existence of the Higgs field, which had been proposed nearly half a century earlier, and helped complete the standard model of particle physics. This achievement was just the beginning. Since then, the LHC has continued to deliver insights, refining our understanding of the fundamental forces and particles that make up the universe. Even if future experiments fail to reveal major deviations from the standard model, the sheer depth of knowledge gained from the LHC will have transformed the way scientists approach questions of the most fundamental nature. Building the LHC was never merely about confirming the existence of a single particle. The ambition was far greater. It was about testing the very boundaries of human capability, both in terms of technology and intellectual curiosity. The fact that the LHC is located underground near Geneva, on the border of Switzerland and France, was a decision driven as much by practicality as by symbolism. The choice preserved valuable land above ground, reduced radiation hazards, and created a more stable environment for the sensitive equipment. Yet this decision also served as a reminder of the larger symbolism. The LHC is a testament to humanity's unyielding determination to peer into the deepest layers of reality, to understand what lies beyond the visible, the known, and the familiar. From the first concept sketches to the day when the beams first began circulating in the collider, the LHC was the product of tireless collaboration. Its creation was shaped by the hands of countless scientists, engineers, administrators, and political leaders who made decisions every step of the way. Each hurdle was met with skepticism, each new challenge with a fresh round of logistical considerations. Yet, through perseverance and innovation, the LHC emerged as one of the most audacious and impressive engineering feats in the history of scientific exploration, a shining example of global collaboration at its finest. Its creation marked not just a milestone in the field of particle physics, but also an unprecedented achievement in human cooperation. CERN, the European Organization for Nuclear Research, stands as the institution behind the LHC. Its vision of constructing a massive underground accelerator capable of achieving energies far beyond those of previous machines had roots stretching back to the organization's early days in the 1950s. Over decades, CERN had steadily built its legacy with smaller experiments and accelerators that paved the way for more ambitious projects. The idea of building an underground ring to collide particles at unprecedented energies emerged as the next logical step in the quest for deeper insights into the universe. And this vision was rooted in a long-standing ambition to make Europe a leader in fundamental scientific research, with CERN at the center of that effort. The organization's original founders envisioned a collaborative, multinational effort that would pool resources, both intellectual and financial, across national borders. CERN's growth and success in the decades following its founding reflected this vision. As its membership expanded and its reputation soared, CERN became the nucleus for some of the most significant discoveries in modern physics, from the discovery of neutral currents to breakthroughs in understanding quarks, neutrinos, and force-carrying particles. These triumphs gave CERN the momentum necessary to propose increasingly ambitious projects, leading to the conceptualization and eventual construction of the Large Hadron Collider. The construction of the LHC, however, did not happen in isolation. The LHC was built to fit into the tunnel created for the previous machine, the Large Electron-Positron Collider, LEP, which had already demonstrated the immense engineering capabilities needed to dig a 27-kilometer tunnel. The tunnel was not just an infrastructure project, it was a critical component of CERN's long-term strategy. With careful planning, the LEP tunnel was repurposed for the LHC, a feat that reflected both foresight and resourcefulness. The planning around the tunnel required careful attention to local geography and geology, as engineers needed to navigate a diverse and challenging landscape. Underground rivers, fault lines, and aquifers posed serious challenges. Precision was critical. Any misstep in the alignment of the tunnel could have had catastrophic consequences, as the LHC requires millimeter-level precision to keep its particle beams on track. At the same time, CERN's vision was not just about building an accelerator. It was about creating a global scientific community. From the very beginning, the experiments associated with the LHC were designed to involve hundreds or even thousands of scientists from diverse countries and institutions. The scale of collaboration required for these experiments was unprecedented in the world of fundamental physics, often more akin to the teamwork required for large-scale space missions. Such a colossal effort required that no single nation could undertake it alone. The LHC was structured as a massive international collaboration, ensuring that decisions were made through consensus building and that discoveries would be shared by scientists from all over the world. While this collaborative approach sometimes slowed decision-making, it ensured that the final result would be one of comprehensive expertise and broad support. Construction of the LHC was not just about digging tunnels and building equipment. It required sophisticated techniques, advanced technology, and massive coordination. Engineers and construction crews had to navigate the complex geology of the region, tunneling through layers of rock without compromising stability. The environment posed its own set of challenges, requiring constant monitoring to ensure that underground water systems were not disrupted and that the environmental impact of the construction process remained within acceptable limits. CERN's philosophy of collaboration extended beyond its scientific endeavors. The organization has always recognized the importance of public engagement and the broader societal impact of its work. While the LHC was primarily a scientific endeavor, CERN knew it had to justify its cost to member states and the broader public. To this end, CERN highlighted technological spin-offs from previous projects, such as the development of medical imaging techniques like PET scans, which rely on particle detection methods developed at CERN. Furthermore, the organization emphasized the advances in computing and data management infrastructure that were byproducts of the LHC's enormous data requirements. This approach helped to show that the LHC's impact would not be confined to the realm of theoretical physics, but would also produce tangible benefits in a variety of sectors, including medicine, computing, and networking. As for the LHC's underground location, it was a practical choice as much as it was a scientific one. The collider's depth below the surface shielded it from cosmic radiation and other external disturbances, ensuring that the delicate measurements could be taken without interference. The Earth itself served as a natural barrier to cosmic rays and other types of radiation that could contaminate the data being gathered by the machine. The underground location also served to reduce the footprint of the machine on the surrounding land, which might otherwise have been used for farming, residential development, or protected natural areas. However, the environmental impact of such an immense construction project was not without concern. Engineers worked to ensure that groundwater supplies were not disrupted and that construction noise and dust did not exceed permissible levels. Balancing the needs of the collider with the realities of the surrounding region was a complex challenge and required constant dialogue with local communities and governments. Another key consideration was how to manage the staggering volume of data the LHC would generate. The sheer scale of the LHC's data requirements was unprecedented, leading to the creation of the Worldwide LHC Computing Grid, WLCG. This global infrastructure allows data to be distributed across multiple continents, with each participating institution contributing computing power and storage. The system ensures that no single facility is overwhelmed by the sheer volume of information and allows scientists around the world to access and analyze the data in real time. This global collaboration in data management mirrored CERN's broader approach to research, which emphasized the importance of international cooperation and the sharing of knowledge. It was also a direct extension of CERN's previous work in creating the World Wide Web, a tool originally designed to facilitate communication among researchers that would become a cornerstone of the digital age. As the LHC took shape and began producing results, CERN also worked hard to engage with the public. Open days, public lectures, and educational outreach programs were part of the organization's efforts to demystify particle physics and engage people in the excitement of scientific discovery. These outreach efforts helped alleviate fears and misconceptions, such as the improbable worry that the collider might create black holes capable of swallowing the Earth. They also served to inspire future generations of scientists and engineers, offering a glimpse of the incredible complexities and wonders of cutting-edge science. Looking beyond the LHC, CERN's vision for the future of particle physics remains undimmed. Discussions around even larger colliders, such as the proposed Future Circular Collider, FCC, demonstrate that the pursuit of higher energies and deeper understanding is far from over. The LHC may have opened new doors, but for CERN, the journey of discovery is only just beginning. CERN's vision is not just about the physical marvel that is the Large Hadron Collider, LHC. It is an ongoing commitment to unraveling the universe's most profound mysteries. Despite the awe-inspiring achievement represented by the LHC, CERN is already focused on the future, anticipating the next leaps in both technology and theory. It continually surveys the horizon, evaluating emerging advancements that could guide its next major phase of experimentation. For some critics, however, the pursuit of ever larger colliders seems to reflect an endless cycle of escalation, driven more by the need for bigger and more powerful machines than by genuine scientific necessity. But for CERN and much of the particle physics community, this drive forward is seen as a natural progression in the quest for deeper understanding. As knowledge advances, it opens up new realms to explore, realms that demand instruments of unprecedented power and precision. This mindset that the evolution of technology is inseparable from the evolution of understanding is at the core of CERN's approach to scientific inquiry. Every step forward, every new collider is not just a larger machine, but a leap into the unknown, one that expands the frontiers of what is achievable in the field of high-energy physics. This is not simply about bigger instruments. It's about pushing the limits of human capability and imagination to uncover the most fundamental truths of nature. What is the nature of reality? What forces govern the universe on its most basic level? These are the questions that fuel CERN's work, and each new discovery brings them one step closer to an answer. One of the most remarkable aspects of CERN's mission is its role as an educational powerhouse. The LHC isn't just a tool for theoretical physicists. It is a laboratory where the next generation of scientists, engineers, and thinkers is trained. Thousands of students from around the world conduct research at CERN, contributing to experiments that push the boundaries of what we know. Their doctoral and postdoctoral work takes them deep into the world of particle collisions, data analysis, and cutting-edge detector technology. This hands-on experience at CERN is invaluable, offering them the opportunity to engage in real-world scientific research that most can only dream of. Upon graduation, many of these students leave the world of academia to carry their expertise into other fields. Some venture into the private sector, applying their problem-solving skills and technical acumen to industries such as technology, finance, and engineering. Others take their training to new heights, applying it to fields ranging from medical research to artificial intelligence. This ongoing movement of highly skilled individuals from CERN to the broader world is an often overlooked consequence of the organization's scientific endeavors. While the LHC may be the focal point of research, its true legacy will be seen in the countless individuals whose careers were shaped by their time at CERN. Their impact will ripple out across industries, leading to innovations that transcend the realm of fundamental physics. CERN's contributions go beyond its experiments and discoveries. They reach into the fabric of society itself. The organization's scientific breakthroughs fuel industries, spark new ideas, and inspire future generations. The problem-solving mindset cultivated at CERN, where complex challenges are met with creativity, collaboration, and persistence, permeates society. These skills, honed in the high-stakes world of particle physics, have a far-reaching impact, often in ways that can't be predicted. Over time, this quiet diffusion of knowledge can be seen in the transformative advances that shape everything from technology to finance, healthcare to environmental science. This influence exemplifies CERN's broader vision, that the pursuit of fundamental physics is not an isolated academic exercise, but a driver of both conceptual and practical progress. However, even with its remarkable achievements, CERN has not been without its challenges. The ever-changing landscape of global economics and politics often creates uncertainty around long-term funding. Scientific projects on the scale of the LHC require sustained financial support, which is vulnerable to shifts in public priorities or political agendas. Additionally, the public's interest in fundamental physics is not constant. At times, it wanes, especially when competing scientific fields or economic pressures demand more immediate attention. Yet, despite these obstacles, CERN has proven resilient. By focusing on the immense value that its work brings, both in terms of scientific discovery and its broader societal impacts, CERN has continually been able to secure the support it needs to carry on. The discovery of the Higgs boson in 2012 was not just a scientific triumph. It was a powerful reminder that these monumental experiments can yield direct, tangible insights into the most profound questions about the universe's workings. From a broader perspective, the LHC is not just a piece of scientific equipment. It is a symbol of humanity's audacious ambition to understand the very laws of physics. Its subterranean tunnels are physical manifestations of an idea that by controlling the collisions of subatomic particles, one can peer into the deepest mysteries of nature. It is a monumental endeavor to recreate, even on a minuscule scale, the extreme conditions that existed just after the Big Bang. The energy and temperatures involved in those early moments of the universe were so high that they allowed quarks, gluons, and other exotic particles to exist freely. As the universe cooled, these particles condensed into the stable matter that makes up the world around us. By recreating these conditions in the LHC, scientists can observe how the universe evolved, almost as if peering backward in time to its earliest moments. But it is not only the collisions themselves that are the focus of attention. It is the complex detectors, such as ATLAS and CMS, that capture the aftermath of each collision. These detectors are marvels of engineering, designed to track and record the cascade of secondary particles produced in each high-energy interaction. With each collision occurring at the rate of hundreds of millions per second, scientists are able to observe phenomena that have never before been seen in the lab. Some of these particles, created in the extreme conditions of the collision, may never appear under normal conditions, providing rare glimpses of the exotic states of matter that existed in the first moments of the universe's existence. Building a machine of the LHC's scale is an immense engineering feat. The journey of the protons begins in a bottle of hydrogen gas, where electrons are stripped away, leaving bare protons that are then fed into a series of smaller accelerators. These accelerators gradually increase the proton speed until they are traveling at nearly the speed of light. From there, they are funneled into the LHC, where they are sent racing around a massive 27-kilometer circular tunnel. To keep the protons on track, powerful superconducting magnets are employed, cooled to temperatures approaching absolute zero, to ensure they remain precisely aligned as they reach energies once thought to be unattainable. Ultimately, the collisions that occur inside the LHC are the culmination of decades of research, technological innovation, and international collaboration. They represent humanity's ongoing effort to understand the universe not just in terms of its observable phenomena, but at the most fundamental level of its existence. The LHC is in many ways the embodiment of the spirit of scientific exploration, an unyielding drive to understand how the universe works at its most basic and mysterious level. It is a quest that transcends borders, cultures, and disciplines, bringing together scientists and engineers from around the world in a shared effort to solve some of the greatest puzzles of nature. The legacy of the LHC, while monumental in its own right, may eventually be surpassed by even larger machines or revolutionary breakthroughs in theory. Yet the vision that brought the LHC into existence, the belief that exploring the unseen realms of the universe is a shared endeavor with immeasurable value, will persist. As long as the questions remain, so too will the spirit of curiosity that drives humanity to seek the answers, no matter how elusive they may be. And in the years and decades to come, the quest for knowledge that started beneath the Swiss-French border will continue to inspire the next generation of explorers, thinkers, and dreamers, all united in their pursuit of the ultimate question: how does the universe work? The journey begins with protons, small and seemingly insignificant particles, yet crucial in unlocking the deepest mysteries of the universe. These protons are injected into the heart of a giant accelerator, the Large Hadron Collider, LHC, where they embark on a complex journey through a vacuum that is even more pristine than the emptiness of outer space itself. Their path is guided by superconducting magnets cooled to temperatures colder than anything found in nature, temperatures nearing the absolute zero limit of 1.9 Kelvin, achieved with the aid of liquid helium. This frigid environment is essential to ensure the magnets operate at peak efficiency, steering the protons in precise tight orbits within the collider. Once inside, these protons are not left to drift aimlessly. They are carefully focused into narrow, tightly packed beams that circulate for hours, often crossing paths at specific interaction points. These interaction points are carefully planned, as the likelihood of a collision is low. Many protons will simply pass each other without interacting. However, the configuration of the beams ensures that those protons which do collide have a higher chance of doing so in a productive way. The beams are engineered with such precision that their diameters are as small as possible at these points, focusing the energy into an incredibly small space where the particles can truly interact. Though these collisions sound like chaotic destructive events, they are anything but. The process is meticulously orchestrated, akin to a finely tuned orchestra. At each of the interaction points, detectors, advanced three-dimensional cameras, are set up to capture every detail of these high-energy encounters. These detectors are not passive. They are sophisticated, using cutting-edge electronics and real-time computing systems to analyze the data as it streams in. The detectors are able to discern which events are worthy of further studies, storing only the most significant data for later analysis. The collisions themselves, however, are not simple to decode. Unlike electron-positron collisions, which involve elementary particles, proton collisions are far more complex. Protons are composite particles made up of quarks and gluons, which share the total energy of the proton. Thus, the energy available in a proton-proton collision depends on which specific quarks or gluons happen to collide. This variability is a major challenge in interpreting the results. To manage this, physicists rely on theoretical models known as parton distribution functions, which predict how a proton's momentum is divided among its constituent particles. While these models add complexity, they also open the door to new discoveries, as they allow for a wider range of possible outcomes, including the creation of new particles that might explain some of the universe's greatest mysteries, such as dark matter or the elusive Higgs field. Operating at such extreme conditions, the LHC itself faces challenges. The superconducting magnets create intense magnetic fields, but they are delicate. Any malfunction, such as the sudden loss of superconductivity, a phenomenon known as a quench, can have serious consequences. The cost of repairs and the downtime required to fix the system are substantial. To prevent such issues, scientists and engineers work around the clock, monitoring the stability of the system with incredible precision. The experiments are carefully planned, with scheduled periods of maintenance and upgrades in between runs. During these pauses, data from previous experiments is analyzed, and improvements are made to the accelerator and its detectors, ensuring that each new run can achieve even greater precision. One of the most significant achievements of the LHC was the discovery of the Higgs boson in 2012. This momentous event marked the culmination of decades of theoretical work and experimental efforts. The Higgs boson had long been a missing piece in the standard model of particle physics, which explains how fundamental particles interact with one another. The discovery was based on the analysis of the decay patterns of particles produced in proton-proton collisions, a painstaking process that required immense computing power. While the Higgs boson has been popularized in the media as the God particle, many physicists consider this label to be misleading. Nonetheless, the discovery confirmed a critical aspect of the standard model, reinforcing our understanding of the forces that govern the universe. However, operating such a colossal machine comes with a steep price. The LHC is incredibly expensive to maintain, and funding often requires international collaboration. Critics sometimes argue that the costs outweigh the benefits, but supporters point out that fundamental research has historically led to transformative technologies, even if the journey from discovery to practical application takes time. Whether or not the immediate returns justify the costs, one thing is clear: smashing protons together remains a powerful tool for exploring the fundamental nature of the universe. In fact, plans are already in motion for even larger colliders, designed to probe beyond the standard model and uncover deeper layers of physics. Each new step in the development of particle colliders brings us closer to answering questions that have eluded scientists for centuries. Will we find new particles that explain the mysteries of dark matter? Can we understand the true nature of the Higgs field or the behavior of neutrinos? The next generation of colliders promises to answer these questions, and perhaps some that have yet to be conceived. Beyond the technology and the science, the LHC is also a testament to international collaboration. Thousands of scientists, engineers, and technicians from all corners of the globe come together to work on the project. Each brings a unique set of skills, from advanced physics to cutting-edge computing, to make the LHC a reality. Cultural and linguistic barriers are overcome by a shared commitment to uncovering the mysteries of the universe. The work is intense, with teams often working around the clock during collider runs, ensuring that everything operates smoothly. When a glitch occurs, whether it's a malfunctioning magnet or a glitch in the data pipeline, the pressure is on to resolve the issue quickly. The success of the experiment often hinges on the ability to troubleshoot and solve these problems swiftly. The public's fascination with the LHC is fueled in part by the drama of the endeavor, brought to life in documentaries and media reports. The concept of an enormous underground machine accelerating particles to near light speeds ignites the imagination. Some have even raised concerns about the collider creating miniature black holes that could threaten the Earth. While these fears have been debunked by scientists who assure that any black holes formed would evaporate almost instantly, the concern is understandable. After all, the energies involved in proton collisions are enormous, and the idea of creating black holes in a lab is both awe-inspiring and terrifying. But physicists point to the natural cosmic rays that hit Earth every day, with energies far greater than those produced in the LHC without causing any harm, suggesting that the experiments conducted at the LHC are safe. At the heart of all these collisions is a simple yet profound question. How does matter behave under extreme conditions? Each collision is an opportunity to ask the universe this question, and each result offers a potential answer. The data collected is analyzed in minute detail, providing a snapshot of how the universe behaves on its most fundamental level. And because billions of collisions occur in the LHC, the chances of discovering something rare are astronomically high. Some events may occur only once in a trillion collisions, but with enough data, these rare occurrences can be identified and studied, potentially leading to groundbreaking discoveries. The pursuit of knowledge doesn't stop with the current collider. Future generations of colliders will be designed to operate at even higher energies and greater luminosity, making it possible to probe even deeper into the subatomic world. These advancements will provide an even clearer view into the strange, unexplored realms of physics. But even with all the advances in technology and understanding, the fundamental act of smashing protons together will remain a cornerstone of high-energy physics for decades to come. It is a process that pushes the boundaries of human knowledge, revealing layers of reality that were once hidden from our view. While the energies involved in proton collisions are staggering, they are nothing compared to the ambitions of those who conduct these experiments. Each analysis, each improvement to the collider, and each new set of data refines our understanding of the fundamental laws of nature. Smashing protons may sound violent, but it is a testament to the precision of modern engineering and the boundless curiosity that drives our quest to understand the cosmos. However, increasing luminosity brings with it a set of new challenges that can complicate data analysis. One of the most notable issues is the occurrence of overlapping collisions, where multiple proton collisions happen in close proximity or at the same time, making it harder to isolate individual events. These overlapping collisions or pileup can obscure the finer details of the data, leading to more complex analysis. Despite these difficulties, the scientific community recognizes that the benefits of higher luminosity far outweigh the drawbacks. For physicists pushing the boundaries of discovery, such trade-offs are a part of the process. By increasing luminosity, colliders generate a larger number of particles per second, improving the chances of capturing rare events that may reveal new and unexpected phenomena. Over time, particle colliders undergo continuous upgrades that enhance both energy and luminosity, helping researchers stay at the forefront of scientific exploration. These upgrades are a crucial part of keeping the technology ahead of the increasing demands placed on it. Parts of the accelerator ring are periodically replaced with newer, more robust components capable of handling higher beam currents, which allow for even more powerful collisions. Alongside this, advancements in magnet technology are vital in producing stronger magnetic fields or providing better stability for the beams, both of which are necessary to maintain the precision of the accelerator. Similarly, detectors are regularly updated to maintain or improve the accuracy of measurements. Newer detector systems with enhanced resolution and faster electronics replace older models, ensuring that each collision is recorded with the utmost detail. These upgrades are not performed arbitrarily, but through a meticulous and well-coordinated plan that aims to minimize downtime while maximizing the potential for scientific breakthroughs once the operations resume. Every upgrade, every replacement of an old part with a newer, more advanced one, is a significant step forward in the quest to investigate higher energy scales where unknown particles might be waiting to be discovered. Colliders not only offer the opportunity to search for entirely new particles, but also allow for the study of well-known particles in ways never before possible. Take the top quark, for example. Though it was discovered in the 1990s, its properties continue to be intensely studied, particularly at the Large Hadron Collider, LHC, where measurements are made with increasingly greater precision. This ongoing research is driven by the hope that some deviation from theoretical predictions will be detected. If something doesn't align with what the standard models predict, it could indicate the presence of new physics, a new theory that could potentially extend or even replace the current understanding of the subatomic world. This approach is not limited to the top quark alone. Similar studies are ongoing for the W and Z bosons and the Higgs boson, which was discovered in 2012. Tiny discrepancies in their masses, decay rates, or interactions could point to holes in the standard model, suggesting there's still more to uncover in the depths of particle physics. International collaboration plays a pivotal role in the success of projects like the LHC, enabling scientists from all over the world to contribute their diverse skills and perspectives. Whether working on software development, electronics, or theoretical modeling, every team member plays an essential role in the project's success. Scientists from different countries spend extended periods at CERN, often working side by side with colleagues from different cultures and backgrounds. It's not just the work itself that fosters collaboration. It's the shared experiences, whether over dinner in the cafeteria or during late-night shifts in the control room, that spark new ideas and breakthroughs. The LHC is a living testament to the power of global cooperation, where top-tier engineering merges seamlessly with leading-edge physics. All this is fueled by the collective desire to push the boundaries of human knowledge, knowing that each step forward brings us closer to unlocking nature's deepest secrets. Particle colliders also serve a crucial role in validating or challenging theoretical frameworks that extend beyond the standard model of particle physics. Concepts such as supersymmetry or theories involving extra dimensions make specific predictions that can be tested by the results of particle collisions. If a theorized particle doesn't appear at the expected energy levels and production rates, it forces theorists to reevaluate their models, prompting them to revise their ideas or suggest new alternatives. This interaction between theory and experiment is what drives scientific progress forward. It is the continuous cycle of prediction, testing, and refinement that gradually leads to a more accurate and comprehensive description of the universe. As such, particle colliders like the LHC serve not only as tools for discovering new particles, but also as instruments for refining our theoretical understanding of the universe's fundamental workings. Public interest in these high-energy collisions often stems from humanity's innate curiosity and the desire to explore the unknown. This curiosity, coupled with the hope of discovering new technologies or practical applications, is what has historically driven societies to support large-scale scientific endeavors. From the early days of building telescopes to the monumental achievements of rocket launches, large-scale science projects have always been statements of collective ambition and investments in the future. While the knowledge generated by these projects may initially seem abstract or distant from daily life, its impact can eventually filter into other areas, such as medicine and technology. For instance, technologies developed for particle accelerators have already found practical applications in cancer treatments, medical imaging, and even advancements in computing and materials science. These real-world benefits stem directly from the same research-driven collaborations that aim to uncover the secrets of the universe. Even with all the progress made so far, proton smashing remains a technique in its relative infancy. The scientific community believes that there is still so much left to discover, particularly in areas like dark matter, neutrinos, and the imbalance between matter and antimatter, questions that continue to puzzle physicists. Many researchers are convinced that higher energies or more precise measurements could hold the key to unlocking answers, or at least pointing toward the right questions. The possibility that the next collision could reveal a groundbreaking clue about the nature of the universe is a driving force for those who are working to keep these immense machines running. The enormous effort required to operate and maintain these complex instruments is fueled by the hope that the next step in the journey will reveal a new aspect of reality. When thinking about the ultimate significance of proton collisions, it's worth reflecting on how past breakthroughs in physics have shaped the modern world. For example, quantum mechanics, once thought to be a mysterious and abstract field, is now the foundation of technologies that power modern electronics and computing. Similarly, nuclear physics has given rise to medical imaging techniques and life-saving cancer therapies. While it is impossible to predict exactly what new discoveries will come from current and future particle colliders, history has shown that expanding the frontiers of knowledge ultimately brings unexpected benefits to society. By accelerating protons to near-light speeds and smashing them together, scientists tap into energies that reveal the hidden layers of nature itself. This process has already unveiled the Higgs field, which is responsible for giving many particles their mass and provided insights into the strong force that holds quarks together. As future collisions occur, they may continue to uncover new phenomena, gradually filling in the gaps in our understanding of the subatomic world. While smashing protons might seem like a brute force approach to science, it is driven by rigorous theory, advanced engineering, and sophisticated data analysis. The LHC in particular stands as a testament to human ingenuity and global cooperation, bridging disciplines and nations in pursuit of knowledge. Each proton collision is a new opportunity to learn something previously unknown, and there is a collective sense of anticipation whenever these beams begin circulating. In this way, smashing protons is much more than an experiment. It is an ongoing journey into the unknown, one that pushes the limits of what is possible in our quest to understand the nature of existence. Particle colliders like the LHC generate colossal amounts of data with every high-energy proton collision. When protons collide, they create a flurry of secondary particles, each with its own energy, momentum, and other properties, and these signatures are meticulously captured by advanced detectors. Detectors like ATLAS and CMS are designed with multiple layers of specialized components, each focused on detecting a specific type of particle or energy range. As protons cross paths at an astonishing rate, hundreds of millions of times per second, the resulting data can reach petabytes annually. Handling such massive quantities of data presents one of the most complex challenges in modern science. The process begins with the detectors themselves, which act as enormous three-dimensional digital cameras, each capturing detailed information about the collision event from different angles. The detectors are constructed in layers, with each layer designed to capture specific features of the particles produced in a collision. Some layers are optimized to detect charged particles, while others measure the energy carried by photons or hadrons. When a collision occurs, the detector's electronics record signals from each layer, allowing scientists to piece together the entire event and analyze the properties of the particles involved. Collisions that occur in particle detectors, though frequent, rarely stand out as being particularly significant. More often than not, they represent background processes or established phenomena familiar within the realm of known physics. These types of events don't offer new insights, and if all of them were stored, the sheer amount of data would quickly become unmanageable. The volume of information produced by such collisions would overwhelm data storage systems in mere seconds. To avoid this, sophisticated trigger systems are employed to filter data in real time, allowing only the most promising events to be saved for further investigation. These triggers utilize a multi-stage process, systematically narrowing down the data to ensure that only the most potentially exciting collisions are preserved. The first stage of this filtering process is hardware-based. It quickly analyzes a limited subset of the detector's information, applying basic criteria to determine if an event is worth further investigation. If the event passes this initial level of scrutiny, it is passed along to a more advanced software-based trigger. Here, a much deeper analysis takes place, looking for specific patterns such as high-energy muons or clusters of energy concentrated in particular regions of the detector. This stage helps to identify whether the event exhibits any unusual characteristics that warrant closer examination. By the time this filtering process is completed, the data that survives is drastically reduced, often down to a mere few hundred events per second. While this may seem like discarding valuable information, it is an absolutely essential step in managing the vast flow of data that the detector generates. Even with this rigorous selection process in place, the remaining data is still substantial. The events that do make it through the trigger system are then stored in vast computing facilities spread across the globe. The CERN data center operates a globally distributed network called the Worldwide LHC Computing Grid, WLCG, which connects numerous research institutions and data centers worldwide. This network harnesses the computational power of thousands of machines, enabling physicists to access, store, and analyze the immense data sets. These massive data sets are regularly accessed by physicists who perform complex analyses, hunting through the collision events for telltale patterns that could suggest the presence of new particles or phenomena yet to be understood. It's akin to searching for a needle in an ever-growing haystack, where each new discovery could add another layer of complexity to the search. The haystack never stops growing, and there are countless potential needles to find, some of which may turn out to be incredibly rare or never-before-seen particles. Noise is an unavoidable aspect of any particle physics experiment. Just as with any measurement system, the detectors pick up unwanted signals from various sources. These might include interference from the electronics themselves, natural radioactivity in the environment, cosmic rays passing through the detector, or even other interactions that produce signals that resemble those produced by genuine collisions of interest. The challenge for physicists is to distinguish these false signals from the real ones. This requires a profound understanding of the detector's design and the careful calibration of each subsystem that makes up the overall detection system. Over time, physicists learn to recognize the typical signature of background noise, which helps them separate meaningful signals from random fluctuations or irrelevant processes. One of the most persistent challenges in interpreting collision data is the phenomenon of pileup. When multiple proton bunches, each containing billions of protons, collide in the Large Hadron Collider, LHC, several collisions may occur simultaneously at the same location. The detector captures all of these events at once, and their signals overlap, making it more difficult to isolate and reconstruct the details of any one specific event. Advanced algorithms are required to untangle these overlapping signals and assign them correctly. Despite significant advances in detector timing, spatial resolution, and analysis techniques, pileup remains a challenge, particularly as efforts to increase the luminosity of the LHC continue. The journey from raw data to a conclusive physics result is a long and multi-layered process. The first step in this journey is data reconstruction, where the raw signals detected by the various sensors are transformed into meaningful physical quantities, such as the momentum and energy of individual particles. This requires detailed knowledge of the geometry of the detector and how it responds to different types of particles. Once this initial reconstruction is complete, analysts apply various selection criteria, often called cuts, to isolate events that fit particular patterns. For example, they may focus on events involving two high-energy photons or on cases where multiple jets of particles and missing energy are observed. The goal of these cuts is to reduce background noise while keeping as many of the genuinely interesting events as possible. Once this filtering is done, statistical methods are employed to assess whether the remaining events indicate a new physical discovery or are simply the result of random statistical fluctuations. The standard for claiming a new discovery in particle physics is a significance level of 5 standard deviations, often referred to as 5 sigma. This stringent requirement helps to protect against false positives. Random variations in the data can occasionally produce signals that look exciting, but ultimately turn out to be meaningless. Achieving 5 sigma typically requires a vast amount of data and consistent results from various analysis techniques or detector subsystems. As scientists dive deeper into their analyses, they must confront the reality that noise can easily mask or mimic genuine signals. Physicists devote considerable time to cross-checking their results, developing alternative analysis strategies, and running simulations to ensure that their methods are working as expected. Simulation plays a crucial role in modern particle physics. Sophisticated software packages simulate the physics of collisions and the detector's response under different scenarios. By comparing real-world data to these simulated predictions, analysts can refine their models, identify potential biases, and improve their understanding of background processes. The management of this vast amount of data also requires sophisticated tools for version control, metadata management, and collaboration. Teams of researchers, often working across different institutions and even different continents, rely on these systems to share data and findings. In many cases, different teams will focus on looking for different signatures in the same set of collision events. One team might be searching for evidence of new particles that arise in supersymmetry theories, while another is investigating rare decay modes of the Higgs boson. These teams exchange findings, often through internal notes, workshops, and conferences, and may help each other improve their analysis techniques. The scale of collaboration in these experiments is staggering, but so too is the need for rigorous cross-checking and validation. Every dataset can be interpreted in multiple ways, and the potential for errors is always present. One of the most difficult aspects of working with LHC data is dealing with what physicists refer to as systematic uncertainties. These are potential sources of bias that could arise from imperfections in detector calibration, from theoretical approximations, or from other subtle factors that cannot be accounted for through statistical methods alone. While statistical uncertainty can be minimized by gathering more data or combining multiple measurements, systematic uncertainty is much harder to address. It requires careful and precise calibration, as well as ongoing theoretical work to refine models and ensure that results are as accurate as possible. Effectively handling systematic uncertainties can make the difference between a result that stands up to scrutiny and one that crumbles under further analysis. Even with meticulous care, some processes often mimic the signature of more exciting, groundbreaking events. Take, for example, certain combinations of jets and missing energy. These could easily be mistaken for a new particle decaying into invisible particles. However, this apparent anomaly could simply be the result of standard interactions that have been mismeasured or mislabeled. In the world of particle physics, physicists refer to these misleading occurrences as background. These events represent well-known physics phenomena that can either overshadow or imitate the signals we are trying to detect, signals that could point to new, unexplored phenomena in the universe. This is why sophisticated methods such as advanced machine learning are so essential in today's research environment. Neural networks, boosted decision trees, and other cutting-edge algorithms can classify collision events far more effectively than traditional, simple cut-based methods. This is especially true as the size of data sets continues to grow exponentially. The concept of noise goes beyond just raw data. Theoretical models used to interpret collision events themselves function as a sort of noise filter. When a particular theory predicts that a new particle should appear at a specific energy level, an analysis may be designed to zero in on that energy range. Yet, If the theory is slightly off, or if nature has different plans altogether, these narrowly focused searches may miss what is truly happening. This is why broad, model-independent searches are also crucial. These searches scan a wide range of potential signatures, increasing the chances of uncovering surprises that might not fit neatly within any existing theoretical framework. After carefully sifting through mountains of data and estimating the background noise, a final judgment is made about whether an unusual excess of events could indicate a potential new discovery. If it does, the result undergoes rigorous scrutiny within the collaboration. This verification process can be painstakingly long, with each assumption being challenged and tested in order to ensure that the signal is not just a fluke. Only once the collaboration is satisfied that the signal is robust and genuine does the team announce the potential breakthrough. Even then, other independent collaborations or experiments must confirm or refute the claim, which adds another layer of validation before any discovery can be considered definitive. All of these steps paint a clear picture of the magnitude of challenges scientists face when working with data from high-energy experiments like those at the Large Hadron Collider, LHC. The sheer scale of data collected is so vast that no single researcher can possibly handle it all on their own. This makes distributed computing resources and automated analysis pipelines essential. Noise, in its many forms, can easily camouflage genuine discoveries or generate apparent signals that vanish upon closer inspection. As such, dealing with noise has proven to be a greater challenge than the mere act of collecting the data itself. The demand for efficient data processing and noise reduction has led to significant advancements in computing technology. Techniques for parallel processing, high-throughput data transfer, and large-scale data storage, all initially developed for high-energy physics, have since found applications in fields as varied as climate science, genomics, and finance. In many ways, physicists working on particle collisions have become pioneers in managing the challenges of big data, advancing digital technologies that benefit numerous scientific disciplines. The task of managing and analyzing these data is further complicated by the need for international collaboration. Many high-energy physics experiments involve large, multinational teams, and the data they generate must be shared with the broader scientific community. Some of these data releases are made available to the public for educational purposes and occasionally for independent reanalysis. Striking a balance between openness and the need to protect sensitive analyses is an ongoing challenge. While transparency in data sharing can lead to new insights, it also necessitates specialized software and expert knowledge to properly interpret the data. Simply releasing raw data files isn't enough. Understanding the nuances of this information requires highly trained scientists and advanced computational tools. At the intersection of data and theory, these efforts also influence the trajectory of future experiments. When certain particles or forces remain elusive despite exhaustive data analysis, this failure can provide valuable insight into the next steps. It might guide the construction of more powerful accelerators or more sensitive detectors, paving the way for next-generation experiments. In this sense, the mountains of data and the noise they contain aren't just obstacles to overcome. They also serve as roadmaps for the next wave of research initiatives. If a theory suggests a particular phenomenon exists just beyond current experimental capabilities, this may inspire proposals for new, more powerful accelerators. Conversely, if an analysis reveals unexpected anomalies, it could cause researchers to reconsider their experimental strategies. Sometimes it's not about a complete overhaul, but rather small, incremental improvements in data analysis techniques that turn a marginal anomaly into something worth investigating. As new data is collected and systematic uncertainties are better controlled, a small fluctuation in a distribution might become more pronounced, generating new excitement in the field. However, this new enthusiasm can quickly be tempered by the knowledge that, in particle physics, not every discovery will stand the test of time. A promising signal might disappear with additional data, returning to the long list of false alarms in the history of the field. This cyclical process of discovering potential new physics, getting excited, and then revisiting the results is an intrinsic part of scientific discovery. It embodies the tension between hope and skepticism that is at the heart of working with data on such an enormous scale. There's always a sense of urgency in these experiments. Every collision provides an opportunity to learn something profound about the universe, and the investment of time, resources, and money is immense. Time constraints, limited funding cycles, and even the careers of the scientists involved add further pressure to ensure that these experiments yield valuable results. For early career physicists, postdoctoral researchers, and graduate students, entire theses are often built around specific data sets. Ensuring that the data leads to tangible, meaningful results is critical not only for their academic advancement, but also for securing continued funding and investment in high-energy physics. While the road to discovery is challenging, the payoff can be extraordinary. The discovery of the Higgs boson in 2012 stands as a powerful reminder that, hidden within these mountains of data and obscured by the noise, there can be truly revolutionary insights. This triumph reinforces the importance of analyzing massive data sets in meticulous detail, searching for patterns that might illuminate the deepest workings of the universe. Ultimately, the journey through data mountains and noise is one of relentless refinement. The first pass of analysis can reveal broad trends, but deeper investigations, made possible by refined algorithms, updated calibrations, and larger data samples, can uncover subtleties that were previously hidden from view. It's a marathon, not a sprint. Researchers must remain patient, methodical, and diligent, double-checking their results, exploring alternative interpretations, and ensuring that their conclusions rest on firm, solid ground. In the end, these mountains of data and the noise that accompanies them are not to be feared. Rather, they reflect the incredible richness and complexity of the subatomic world. The fact that so many collisions occur, each with its unique signature, reveals just how vibrant and intricate the world of particle physics truly is. Buried within all these events are the stories of how fundamental particles behave, combine, and sometimes surprise us with their properties. The challenge of filtering out the noise only makes those rare, game-changing discoveries that much more rewarding. In the end, it is the successful navigation through this chaotic torrent of information, generated when protons smash into each other at near light speed, that is a true test of mastery in the field of particle physics. The excitement in particle physics often builds around unexpected signals that emerge from the noise. These signals, often in the form of excesses or deviations from well-established theoretical predictions, have the potential to herald the discovery of new particles or even physics beyond the standard model. The dream of uncovering the next big breakthrough drives researchers to spend countless hours poring over collision data, hoping for a glimpse into something profound. Yet history has shown that not every bump in the data leads to a new discovery. False alarms, dead ends, and misinterpretations are an unavoidable part of the scientific journey. Nature, as scientists have come to understand, is often more subtle and elusive than anyone could have imagined. One famous example of a false alarm occurred during the search for the Higgs boson. Years before its official discovery in 2012, smaller colliders, such as the Large Electron-Positron Collider and the Tevatron, had observed small excesses that seemed to hint at the presence of the Higgs. Each time, the hopes of the scientific community soared, only to be dashed by further data that showed these bumps were merely statistical fluctuations. While these near misses were disheartening, they also spurred researchers to refine their methods, improve their understanding, and push for higher energies. Ultimately, this relentless pursuit of knowledge culminated in the LHC's definitive observation of the Higgs boson, a triumph that reinforced a core truth in high-energy physics. One or two intriguing events are rarely enough to claim a discovery. However, a seemingly innocuous glitch in a timing cable and a malfunctioning clock oscillator led to a minuscule error that made neutrinos appear faster than the speed of light. Once these flaws were corrected, the result aligned with the universal speed limit, and the scientific community collectively exhaled a sigh of relief. It was a reminder that extraordinary claims require extraordinary scrutiny. The incident underscored a fundamental truth in science. The process of discovery is often paved with missteps, recalculations, and reevaluations. Another recurring theme in scientific exploration involves signals that emerge in one experiment but fail to be replicated in others. Replicability is a cornerstone of the scientific method. When a phenomenon appears to have been observed, it must be reproducible under identical conditions in different setups, detectors, or experimental environments. If independent investigations fail to reproduce the result, the initial discovery is often dismissed as a statistical anomaly or an error that is unique to the particular experimental conditions. This pattern has been observed in various fields, and notably in dark matter detection experiments. One research team might report an intriguing signal, only for other teams, conducting similar experiments in different locations, to find no trace of the same effect. This contradiction forces scientists to revisit their hypotheses, refine their techniques, and dig deeper into the data, often leading to new insights and a greater understanding of the challenges they face. This type of false alarm is not limited to experiments alone. It extends into the realm of theoretical physics as well. Theoretical physicists develop models predicting the existence of new particles or novel signatures in the data. When experiments are conducted and no evidence for these predicted particles or phenomena materializes, these models must either be discarded or significantly revised. One of the most prominent examples of this is supersymmetry, SW. Early versions of SUSY predicted the existence of new particles that should have been detectable by the Large Hadron Collider, LHC. Yet, after years of experiments and data analysis, large swaths of the SUSY parameter space have been ruled out. While it remains possible that SUSY could manifest at higher energies or in more subtle forms, many of the earlier, more popular iterations now appear to be dead ends. In the world of theoretical physics, dead ends can be as frustrating as experimental false alarms, yet they often serve a crucial purpose. They force physicists to refine their ideas, reconsider their assumptions, and ultimately push the boundaries of their understanding. On occasion, an anomaly may persist for a time, fueling intense speculation and excitement among physicists. The initial signal might show up as a modest excess of data at a particular energy level. Researchers scrutinize the data, double-checking their methods, verifying their calculations, and holding internal discussions. A paper might even be released, tentatively suggesting that this anomaly could point to something significant, a hint of new physics, perhaps. As the news circulates through the scientific community, theoretical physicists begin drafting papers, proposing exotic new models to explain the unexpected signal. These discussions spark excitement, and many wonder if this could be the breakthrough that will rewrite the rules of physics. However, as more data is collected, the signal fades away and the initial excitement dissipates. What was once a tantalizing hint of something revolutionary turns out to be just another fluctuation, another statistical blip in the vast sea of data. The thrill of the chase gives way to the sobering reality that the anomaly was not the harbinger of a new discovery, but rather a natural fluctuation within the noise of the data. These instances, though initially disappointing, are vital to the scientific process. They serve as proof of the strength and integrity of the scientific method, which relies on rigorous peer review, meticulous checks, and replication attempts. Over time, the false alarms are filtered out, leaving only the most robust signals that can withstand the scrutiny of the scientific community. One of the most celebrated examples of this rigorous process is the discovery of the Higgs boson. In the early days, various experiments produced hints of a particle with a mass near the predicted value of the Higgs boson, but none of these results were definitive. It wasn't until the LHC had gathered enough data and both the ATLAS and CMS experiments independently confirmed the existence of a particle with a mass that matched the Higgs boson that the discovery was considered definitive. False alarms and dead ends also play a critical role in training the next generation of scientists. Graduate students, postdoctoral researchers, and young physicists are often assigned to chase down these elusive anomalies. In doing so, they learn invaluable lessons about data analysis, systematic checks, and the intricate nature of experimental physics. These lessons not only prepare them for future discoveries, but also equip them with the skills needed to distinguish between genuine phenomena and artifacts or errors. Such skills are highly valued, not only in academia, but in fields like finance, technology, and data science, where complex data analysis is essential. The willingness to pursue anomalies is one of the defining characteristics of the scientific community. Even the smallest possibility that a signal could indicate something profound motivates researchers to examine it closely rather than dismiss it outright. This open-mindedness, tempered with a healthy skepticism, ensures that extraordinary claims are only accepted after they have been rigorously tested and substantiated. False alarms, though sometimes frustrating, expose the delicate balance between the eagerness for discovery and the caution necessary to avoid jumping to conclusions. This tension between optimism and skepticism ultimately strengthens the field of physics. It ensures that breakthroughs are based on solid, reproducible evidence and not on unverified claims. However, the media often amplifies the tension between these two forces. Hype can build around early, unconfirmed findings, and when these anomalies fail to materialize into breakthroughs, the public's interest often wanes. This can create a sense of cynicism about the reliability of scientific research, as though scientists are constantly crying wolf. In reality, the scientific community tends to communicate these findings with great caution, carefully pointing out the provisional nature of early results until they are confirmed. It is often the media, in its quest for sensational headlines, that exaggerates the significance of unverified claims. As time goes on, particle physics institutions have become better at managing expectations, communicating the uncertainties inherent in preliminary results, and clarifying that anomalies must be validated before they are considered significant. One reason for the prevalence of false alarms lies in the sheer volume of data that modern experiments generate. In experiments like those at the LHC, billions of collisions are recorded, and even the most unlikely events can appear regularly within this vast dataset. Particle physics is inherently statistical, and with large datasets come random fluctuations that can mimic real effects. Additionally, the constant drive to explore new territories of energy or precision means that detectors and analytical tools are pushed to their limits, where systematic errors are more likely to occur. The interplay of vast datasets and cutting-edge technology naturally results in occasional missteps on the way to genuine discoveries. Dead ends can also reveal deeper limitations in our understanding of the laws of nature. The standard model of particle physics, while incredibly successful, is known to be incomplete. It cannot explain certain phenomena, such as dark matter, dark energy, or the masses of neutrinos. Scientists continue to propose extensions to the standard model to address these gaps, but many of these ideas have yet to yield direct experimental evidence. These theories often stall in the face of experiments that lack the necessary sensitivity or energy scales to test them directly. Despite the fact that many of these ideas remain unproven, they are not necessarily wrong. They simply await the development of new tools, more powerful accelerators, or more sensitive detectors that will eventually be able to probe these deeper questions. In the meantime, the search continues, with each failed experiment serving as a stepping stone toward future breakthroughs. Even in the face of repeated failures, the particle physics community remains undeterred. False alarms and dead ends are not viewed as setbacks, but rather as necessary challenges in the quest for a deeper understanding of the universe. These experiences drive improvements in experimental designs, refinement of theoretical models, and a more nuanced understanding of the complexities involved. Each null result or retraction helps to focus the scientific community's attention on the questions that truly matter. It is through this iterative process of testing, rejection, and refinement that genuine breakthroughs ultimately emerge. The bar for discovery in physics is set high, ensuring that only the most reliable and reproducible findings receive widespread recognition. The cycle of excitement, followed by disillusionment, punctuated by occasional triumphs, shapes not only the scientific process, but also funding priorities and collaborations. Large-scale projects require significant resources, and funding agencies demand results. While a string of null findings can be frustrating, the scientific community can point to past successes, like the Higgs boson discovery, to demonstrate the long-term nature of fundamental research. The process of scientific discovery, with all its false alarms and dead ends, is a long game. The occasional setbacks only serve to highlight the monumental significance of the moments when the pieces finally fall into place. In the grand scheme of things, false alarms and dead ends are byproducts of a system working as it should. Science proceeds by trial and error, with each step building on previous knowledge. The fluctuations and anomalies that dissolve under scrutiny are not failures. They are lessons that sharpen experimental techniques, refine theoretical models, and guide future research. Over time, these lessons accumulate, driving the field forward. No one enjoys the disappointment of realizing that months of hard work have led to a dead end, but these experiences are invaluable. They clarify the landscape of scientific exploration, making future searches more focused and informed. For enthusiasts and outsiders alike, it's essential to understand that every supposed breakthrough in particle physics is subject to a rigorous vetting process. Claims might be shared in preprint form, discussed at conferences and circulate in the media. But the true verdict is only given once they pass through peer review and receive official confirmation from the research collaborations involved. This lengthy, methodical process is not a weakness of the field, but a strength. Each false alarm, each failed hypothesis is a stepping stone toward more solid theories, sharper instruments, and ultimately more profound discoveries. The journey to the Higgs boson's discovery is a perfect illustration of how, despite countless false alarms and dead ends along the way, the persistence and diligence of the scientific community eventually led to one of the most significant breakthroughs in modern physics. The announcement on July 4, 2012 at CERN was a landmark moment in the history of science, not just because it confirmed a long-predicted particle, but because it exemplified the power of the scientific method to sift through noise and find the signal of truth. On July 4, 2012, a day that would become etched in history as one of the most significant moments in modern science, the world waited with bated breath. That date was chosen for the monumental occasion of presenting the preliminary findings from years of meticulous research and exhaustive analysis conducted by the teams working on the ATLAS and CMS experiments at CERN. The anticipation that hung in the air was so thick that it seemed almost tangible, palpable among physicists, journalists, and science enthusiasts who had been following every thread, every piece of data that might hint at the discovery of the Higgs boson, the elusive particle that had remained a mystery for decades. This was not just a scientific discovery, it was the culmination of an ambitious global pursuit that had gripped the scientific community and beyond. On that fateful morning, the grand auditorium at CERN was packed with the brightest minds in the field of physics, all awaiting the presentation of data that could change the course of science forever. From within the auditorium and across the world, countless viewers tuned in through live streams to witness the outcome. The press conference, which had been meticulously orchestrated, was a pivotal moment. It was poised to either confirm the existence of the Higgs boson, a particle whose existence had been postulated but never observed, or deflate the intense excitement if the data fell short of the statistical significance required for a legitimate discovery. For those involved in the research, there was no shortage of caution. While the data hinted at something remarkable, most experts refrained from outright declaring a discovery until the crucial 5 sigma standard was met. This threshold, which indicated a statistical certainty of 1 in 3.5 million that the result was not a fluke, had become the gold standard for declaring a discovery in particle physics. It was a rigorous benchmark, ensuring that only results with extreme confidence would be announced to the world. The atmosphere inside the CERN auditorium was unlike any typical scientific gathering. Physicists who are rigorously trained to approach data with sober caution found themselves grappling with emotions they rarely let surface. This moment had been years in the making, and the discovery of the Higgs boson, if confirmed, would be the realization of a theory that had been proposed in the 1960s, but had eluded verification for more than half a century. Among the distinguished attendees were Nobel Prize winners, prominent heads of major physics institutions, and perhaps most poignantly, Peter Higgs himself, whose theoretical work had laid the foundation for this search. These were individuals who had dedicated their careers, their lives, to the pursuit of understanding the fundamental workings of the universe. The tension in the room was palpable as scientists prepared to reveal the data. The presentations began first with Atlas, followed by CMS. Researchers took turns outlining their findings, presenting detailed graphs and statistical models, energy peaks, background estimates, and sophisticated analyses, carefully scrutinized by those in attendance. While to the untrained eye, these graphs might have appeared to be little more than colorful squiggles, to the physicists in the room, every curve, every peak, and every data point carried profound meaning. These shapes were not mere lines, they were signals from the universe itself, offering the possibility of a discovery that would reshape the understanding of physics. The key question that loomed over the presentations was whether the data would align with the predicted signature of the Higgs boson, specifically in the mass range that theorists had long anticipated. For months leading up to the announcement, partial datasets had suggested that if the Higgs boson existed, its mass was likely to fall within the range of 125 to 126 giga-electron volts, GeV. With every new slide that appeared on the screen, there were murmurs of excitement as the data hinted at the possibility of a clear signal, a peak rising above the background noise. But it wasn't until one of the lead scientists, with a calm demeanor but unmistakable significance in their words, confirmed that the data had crossed the crucial 5 sigma threshold that the realization struck. A new particle had been observed, and it was consistent with the Higgs boson at approximately 125 GeV. The crowd, already on the edge of their seats, erupted into applause. It was a rare moment in the world of science, where the celebration of data and discovery transcended the usual calm and collected atmosphere of a scientific conference. For a brief moment, the room felt less like an auditorium and more like the final act of a grand concert, a celebration of an achievement years in the making. Some even found themselves wiping away tears, overwhelmed by the enormity of the moment. Decades of theory, countless billions of dollars in investment, and the efforts of thousands of scientists around the world had all converged on this single point in time. Peter Higgs, the man whose name would forever be associated with this discovery, sat quietly in the audience, a reserved figure in the midst of the joyous chaos. When the press conference transitioned to a question and answer session, reporters and fellow scientists alike turned to him, eager to hear his thoughts. Known for his shyness and reluctance to seek the limelight, Higgs nonetheless recognized the historic significance of the day. With humility and grace, he expressed his gratitude to everyone involved in the search, extending his thanks not only to the theorists who had helped develop the Higgs mechanism, but also to the engineers, technicians, and administrators who'd worked tirelessly to build and maintain the Large Hadron Collider, LHC, and its detectors. He also acknowledged those theorists who had passed away before seeing their theories confirmed, a poignant reminder that many of those responsible for this breakthrough were no longer around to witness it. The news of the discovery soon spread beyond the scientific community, making headlines around the world. The term God particle, though disliked by many physicists for its sensationalism, became the go-to phrase in media coverage, capturing the public's imagination. Major news outlets rushed to explain the discovery in terms that could be understood by a general audience, but even the most simplified explanations couldn't fully capture the drama and significance of what had just occurred. A particle that had once been a theoretical abstraction, a name on a chalkboard, was now confirmed to exist. The Higgs boson had been found. The announcement on July 4th was timely, coinciding with the American Independence Day holiday, which gave journalists in the US a rare opportunity to cover a scientific story of immense significance when their attention would usually be diverted to other stories. Some speculated that the timing of the announcement was no accident, that CERN had deliberately chosen the date to maximize media coverage, but officials at CERN maintained that the date had simply worked out. They had promised updates around mid-year, and the data was ready when it was. After the official presentations and media interviews concluded, the excitement did not subside. In fact, it intensified. Physicists from around the world turned their attention to the newly released data, poring over every detail. While everyone agreed that a new particle had been discovered, the question remained: was this truly the Higgs boson as predicted by the standard model of particle physics, or could it be something else? Could this discovery be the first clue in a much larger puzzle, opening the door to new physics beyond the standard model, perhaps uncovering evidence of supersymmetry or hidden dimensions? What was certain was that the discovery marked a monumental milestone in physics. It was celebrated as one of the greatest breakthroughs of the past 50 years. The scientific community, including students and postdocs who had spent countless hours analyzing collision data, felt an overwhelming sense of accomplishment. Their efforts had contributed to confirming one of the fundamental building blocks of the universe. In the days following the announcement, the discovery continued to make waves in the media. CERN's servers struggled to keep up with the overwhelming traffic, and social media platforms were ablaze with excitement. Political leaders worldwide congratulated the teams at CERN, marveling at the power of international collaboration. In some countries, the hope was that this discovery would ignite renewed interest in STEM fields, inspiring future generations of scientists and justifying the enormous financial investments in projects like the LHC. Conferences, workshops, and papers quickly followed the announcement. The world's physicists delved deeper into the technical aspects of the discovery, examining every angle of the data. As with any groundbreaking result, questions remained. The standard model had been a well-tested framework, but it was not complete. What more needed to be measured to fully understand the nature of the newly discovered particle? Could it be a gateway to new, unknown physics? These questions would continue to drive research in the years to come. The announcement on July 4th, 2012 was more than just a scientific breakthrough. It was a moment of global unity, where the collective effort of thousands of scientists and engineers across the world had come together to answer one of the most profound questions about the universe. Even critics who had questioned the immense cost of the LHC acknowledged the significance of the result. The Higgs boson was no longer just a theoretical concept, it was real. And its discovery stood as a testament to humanity's ability to overcome challenges, push technological boundaries, and answer some of the most fundamental questions about the nature of reality. In the years since that historic day, the impact of the discovery of the Higgs boson has continued to reverberate. It remains a defining moment in the history of science, a reminder that even in an age of rapid technological advancement, there are still mysteries to unravel, and that the pursuit of knowledge will continue to inspire wonder for generations to come. For those who were in that CERN auditorium on July 4th, 2012, the experience remains a once-in-a-lifetime memory, a moment when the boundaries of human knowledge expanded before their eyes, and the future of physics was forever altered. Reporters around the world flocked to capture the essence of a moment that marked a critical juncture in scientific history. Their stories captured not just the technical intricacies, but also the profound human passion driving the search. In hindsight, the announcement made on July 4th, 2012, stood as both a culmination and a new beginning. It marked the end of a decades-long quest for the Higgs boson, but at the same time, it opened up vast avenues for further inquiry. The discovery set in motion a new era of exploration into the particle's properties, its place within the standard model of particle physics, and the tantalizing possibility that it might hold clues to mysteries beyond the established framework. In the aftermath, talk of future collider projects, vast new data sets, and the broader implications for understanding the universe became the talk of the town. That historic announcement, a brilliant flash of discovery, was far from the final word in particle physics. Rather than serving as a closing chapter, it felt more like the discovery of an entirely new room within the grand mansion of scientific inquiry. This discovery prompted scientists to ask themselves, what else might be hiding just beyond the next corner? For a moment, the world found itself captivated by an achievement that seemed both monumental and mysterious, and one that triggered a wave of curiosity, awe, and philosophical wonderment about the very fabric of existence. The days and weeks that followed saw a flood of articles, interviews, and feature stories examining the significance of the Higgs boson. Public interest in particle physics surged as people sought to understand the fundamental principles of the Standard Model, the concept of fields, and why discovering a particle so fundamental to our understanding of nature was of such monumental importance. Educators took to classrooms, using the discovery as an inspiration to teach not just physics, but the value of human collaboration. They explained how it took the combined efforts of thousands of scientists and engineers working together across decades to reveal one of nature's deepest secrets. Throughout the remainder of 2012, scientists at CERN worked tirelessly to refine their initial findings. The initial excitement in the media may have subsided, but in the scientific community, the real work was just beginning. Peer-reviewed journals began to publish in-depth analyses detailing the ways in which the new particle had manifested in the data captured by the ATLAS and CMS experiments. What remained to be fully determined was how precisely the particle's various properties, its spin, parity, and decay channels, matched the theoretical predictions of the Higgs boson. But one thing was clear. On July 4, 2012, the Higgs boson had gone from being a theoretical placeholder in physics textbooks to a confirmed reality. Over time, that day became emblematic of what global collaboration can achieve. Institutions from around the world had come together to design, build, and operate the Large Hadron Collider, LHC. They had overcome engineering challenges unlike anything seen before, processing vast amounts of data and creating technologies that would push the boundaries of human knowledge. The announcement on July 4th was the payoff that everyone involved had worked toward for so long. The excitement was so widespread that even those who had little interest in physics found themselves drawn into the story, awestruck by the magnitude of confirming a piece of the universe that had existed only in the realm of hypothesis for so long. As we look back at the major scientific milestones of the 21st century, it's clear that July 4th, 2012 will forever be remembered alongside achievements like landing on the moon or decoding the human genome. Each of these milestones represents a leap forward in human understanding, a moment when we crossed an important threshold in knowledge and capability. For particle physics, the discovery of the Higgs boson did more than conclude a half-century-long search. It validated a revolutionary concept, that empty space is far from empty. It set the stage for deeper inquiries into the nature of mass, the future of fundamental research, and the ways in which society values scientific ambition. Of course, the moment of discovery wasn't limited to a single day. The data collection, analysis, and verification of the Higgs signal had taken place over many months of meticulous work. But the public announcement on July 4th became the moment that would live on in collective memory. It captured a snapshot of a scientific journey that had required years of labor, tens of thousands of people, and billions of dollars to bring to fruition. It was the day when the world learned about something that had been silently present behind the scenes of the universe, influencing the very matter that makes up everything around us. What makes this discovery so compelling, however, is that it was more than just the identification of a new particle. It was a testament to humanity's unyielding curiosity and determination to answer some of the most profound questions we can ask. The Higgs boson was the key to a much larger puzzle, one that continues to unfold as scientists push forward in their investigations. Using cutting-edge technology, mathematics, and a spirit of global collaboration, scientists at CERN had succeeded in peering into the heart of matter itself. The announcement on July 4th, 2012, demonstrated that humanity's thirst for discovery knows no bounds. It showed that with the right combination of imagination, testing, and perseverance, breakthroughs that seem impossible today may become tomorrow's groundbreaking discoveries. The eruption of applause that filled CERN's auditorium was not just for a particle. It was for the culmination of a dream, shared by thousands across the globe. It reminded us that, even in the most abstract corners of scientific exploration, there is a universal appeal to the spirit of discovery. It's a message that resonates with people from all walks of life, from curious students to seasoned physicists, because it speaks to our shared drive to understand the world we live in. In the years following the discovery, the significance of the Higgs boson continued to ripple through the scientific community and beyond. After decades of speculation, rumors, and painstaking data analysis, the confirmation of the Higgs particle finally solidified the Standard Model as a powerful framework for understanding the forces and particles that govern our universe. But the story didn't end with the discovery itself. Far from it. Scientists knew that this was just the beginning. More work needed to be done to fully understand the properties of this elusive particle and its implications for the future of physics. The path to discovering the Higgs boson involved a detailed and sophisticated process of data collection, analysis, and verification. When the team at CERN first identified the particle, they didn't just observe it in isolation, they traced its presence through its various decay channels. In high-energy collisions, the Higgs boson, if produced, would break down into other particles, such as photons, W bosons, Z bosons, or pairs of fermions like bottom quarks and tau leptons. Each of these decay processes left behind a unique signature in the detectors of the LHC. What made these signals so crucial was their relative purity. Some decay channels produced cleaner data with less background noise, allowing for a clearer identification of the Higgs boson. The most significant of these channels were the diphoton decay, in which the boson decays into two photons, and the four-lepton decay, which involved the Higgs decaying into two Z bosons, which then broke down into pairs of leptons. These signals stood out in the data with such clarity that they couldn't be ignored. A peak appeared around 125 gigaelectron volts GeV, indicating a significant excess of events above the expected background level, a clear sign that a new particle had been produced and decayed in a way that matched predictions for the Higgs. Both the ATLAS and CMS experiments at CERN approached the data analysis independently, each employing its own algorithms and methods. But when both teams arrived at the same conclusions, it strengthened the case beyond measure. The consistency of the results was key, bolstering the belief that what they had observed was indeed the long-sought Higgs boson. In the beginning, the data collected from the experiments provided only the faintest hints of a discovery. It confirmed the existence of a particle, a boson, but the details remained uncertain. The particle's mass and decay rates were clear, but to definitively identify it as the Higgs boson, as predicted by the Standard Model, it had to meet a number of other stringent criteria. For instance, the particle had to exhibit a specific set of quantum characteristics, including spin and parity. The Standard Model predicts that the Higgs boson has zero spin and positive parity, which makes it distinct from other potential bosons. However, the earliest results from the experiments did not conclusively confirm these properties. What followed was a painstaking series of measurements and analyses as scientists sought to test the spin of the particle, its decay modes, and its coupling strengths to other known particles. Over time, the data began to align more closely with the predictions made by the Standard Model, offering growing confidence in the particle's true identity. At first, however, physicists were cautious. Even though the initial data suggested the presence of the Higgs boson, terms like Higgs-like particle and consistent with the Standard Model Higgs were commonly used. This caution was not an effort to hedge, but rather a reflection of the scientific process itself, one that values precision and thorough verification. In the realm of physics, confirming all possible properties of a particle before drawing conclusions is paramount. Even after accumulating a considerable body of evidence, many scientists kept an open mind, considering the possibility that the particle could be a version of the Higgs predicted by theories beyond the Standard Model. These alternative theories, such as those invoking supersymmetry, propose the existence of multiple Higgs-like particles or a version of the Higgs boson with additional properties not accounted for in the simplest model. This uncertainty was amplified by the fact that the Higgs boson was predicted to interact with other particles in specific ways, and early data showed that it indeed coupled to known particles in a manner consistent with the Higgs field's predictions. One of the key elements of the Higgs mechanism, the theory behind the Higgs field, is that it provides mass to fundamental particles through interactions. For the discovered particle to truly be the Higgs boson, its interactions with particles like the W and Z bosons, as well as fermions such as quarks and leptons, would need to match the Standard Model's predictions. Early measurements suggested that this was the case, but additional experiments at the Large Hadron Collider, LHC, were necessary to refine the data and confirm the strength of these coupling interactions. As the experimental data continued to accumulate, the particle's characteristics began to align more and more with the properties expected of the Higgs boson. This was a momentous revelation in the field of particle physics, for the Higgs boson was the final missing piece of the Standard Model, and its discovery promised to answer a long-standing question: why do fundamental particles have mass? Before the discovery, scientists had struggled with the question of how particles like the W and Z bosons, which mediate the weak force, could possess mass. The symmetry of the electroweak force predicted that these particles should be massless unless there was some mechanism that could break this symmetry. The Higgs field was introduced as the mechanism to explain this, but its existence implied the need for a new particle, the Higgs boson. The Higgs field, in this sense, became the star of the show, the theoretical foundation for how particles acquire mass, while the Higgs boson was the tangible, observable manifestation of that field. The discovery of this particle provided strong experimental evidence for the reality of the Higgs field. Naturally, many wondered how scientists could be so certain that this particle was truly the Higgs. The answer lay in the precision of the Standard Model's predictions, which had been made decades earlier. The model offered exact estimates of how strongly the Higgs boson should couple to known particles, as well as predictions for its likely decay rates and branching ratios. Over time, the data collected from the LHC confirmed these predictions with remarkable accuracy. Another clue that bolstered confidence in the discovery was the particle's mass, around 125 gigaverts. This specific mass range was particularly interesting because it made a variety of decay channels accessible, providing scientists with multiple ways to gather evidence and confirm the particle's identity. The impact of this discovery reverberated across the entire framework of particle physics. The Higgs boson plays a central role in the electroweak symmetry breaking mechanism, which is necessary to explain why the W and Z bosons have mass. Without this mechanism, the Standard Model would predict that these particles should be massless, a prediction that clearly contradicts experimental observations. By confirming the existence of the Higgs boson, scientists verified the Higgs mechanism and, with it, the way in which other fundamental particles acquire mass through interactions with the Higgs field. This was not just a triumph of theory, it was a direct confirmation that a crucial part of the Standard Model was a real physical phenomenon. As the discovery was being announced to the world, physicists often mentioned the 5 sigma requirement, a strict standard for statistical significance. In experimental physics, particularly with data sets as vast as those generated by the LHC, random fluctuations can occur, creating apparent bumps in the data that are nothing more than statistical noise. The 5 sigma requirement ensures that the probability of such a fluctuation being mistaken for a real physical effect is astronomically low. Both the ATLAS and CMS experiments at the LHC reached or exceeded this threshold of significance, making the discovery of the Higgs boson not just plausible, but overwhelmingly likely. At the same time, there was still the question of whether this particle could be part of a larger set of particles, some of which might lie outside the Standard Model. Theories beyond the Standard Model, such as supersymmetry, predicted the existence of multiple Higgs bosons, and the particle discovered at the LHC might have been the lightest of these. Alternatively, there was the possibility that the new boson could display slight deviations from the pure Standard Model predictions, hinting at new physics waiting to be uncovered. As additional data poured in, however, no significant deviations from the Standard Model were found. The particle's properties were remarkably consistent with what was expected of the Higgs boson, and as a result, it seemed increasingly likely that the particle was indeed the one predicted by the Standard Model. This outcome was a source of mixed emotions within the scientific community. On the one hand, confirming the existence of the Standard Model Higgs was a monumental achievement in physics, representing the completion of a theory that had guided research for decades. On the other hand, many physicists had hoped that the discovery would open the door to new and exotic phenomena, perhaps a window into a deeper, more intricate understanding of the universe. Yet, while the Higgs discovery did not reveal new particles or groundbreaking surprises, it solidified the Standard Model in a way that made it nearly irrefutable. It validated the framework that had guided decades of research and provided confidence that the most basic equations describing particle interactions were indeed correct. For years, the Higgs mechanism had been taught in classrooms around the world as a vital part of understanding particle physics. But it was always prefaced with the caveat, if the Higgs exists. Once the LHC confirmed the existence of the Higgs boson, that if was removed, and the Higgs became a cornerstone of modern physics. Textbooks were updated, and the next generation of physicists grew up learning about the Higgs boson not as a hypothetical concept, but as a well-established part of the Standard Model. Beyond the technical and scientific implications, the discovery was a triumph of human ingenuity. The LHC was a feat of engineering and technology, capable of generating such precise measurements that scientists were able to detect a particle that decays almost instantaneously, a particle that cannot be isolated and studied directly. The Higgs boson exists only fleetingly, emerging in high-energy particle collisions and decaying almost immediately into other particles. Detecting it was a remarkable accomplishment, like capturing a faint echo in a vast, noisy room. It required advanced detectors, millions of sensors, high-powered electronics, and sophisticated algorithms to ensure that nothing slipped through unnoticed. So, what did scientists really find? The short answer is that they found a boson that was consistent with the long-predicted Higgs. The slightly longer answer is that the discovery provided direct experimental confirmation of the Higgs mechanism, verifying the Standard Model's explanation for how particles acquire mass. This was a revolutionary step in particle physics, not because it revealed anything fundamentally new, but because it validated the theoretical framework that had guided decades of research. While it did not provide answers to all the mysteries of the universe, such as the nature of dark matter and dark energy, the discovery of the Higgs boson reinforced the foundation of the Standard Model and gave scientists renewed confidence in their understanding of the fundamental forces that govern the universe. The LHC experiments uncovered exactly what they had set out to find, but they did not stumble upon something that would rewrite textbooks. Instead, they confirmed a theory that had stood the test of time and provided the missing link in the puzzle of particle physics. In the world of modern physics, there remains a sense of optimism and anticipation among many researchers who hold out hope that higher precision measurements or collisions at even greater energies might eventually reveal new anomalies or previously unknown particles. These discoveries could potentially push the boundaries of the Standard Model of particle physics even further. At the heart of this ongoing pursuit, however, lies a landmark discovery, the Higgs boson, a particle that was once purely theoretical, but now stands as a concrete manifestation of a field that governs the very nature of mass itself. This field, known as the Higgs field, was hypothesized to permeate the entire universe, interacting with fundamental particles to give them mass. The realization of the Higgs boson, produced in high-energy particle collisions, marks a pivotal moment in the history of science. Discovered at approximately 125 giga-electron volts, or 125 GeVs, the discovery is far more than a mere verification of a theory. It is a confirmation of a cornerstone that has held up the framework of particle physics for over half a century. While the discovery of the Higgs boson did not immediately shatter the established Standard Model or usher in a new era of physics, it solidified the very foundation upon which modern physics rests. This monumental achievement opened the door for further exploration into the unseen realms of subatomic particles, offering a path forward for new discoveries and deeper understanding of the universe. The discovery was not simply about ticking a box on the Standard Model's to-do list. It was about uncovering a profound truth that has broad implications for science, technology, and society as a whole. On a purely scientific level, the Standard Model had long been a remarkably successful theory, explaining the behavior of known subatomic particles. However, it had always had one glaring omission: the Higgs boson. For decades, textbooks had presented the theory that particles acquire mass through interactions with the ubiquitous Higgs field, and that the boson associated with this field was simply waiting to be found. The prolonged absence of this particle led many to speculate that it might be more elusive or difficult to detect than other particles. The eventual confirmation of the Higgs boson, however, did more than just fill in a missing piece of the puzzle. It underscored the deep unity of nature, the interconnectedness of forces and particles that govern everything from the most microscopic to the most cosmic scales. Mass, which is so intrinsic to our daily lives, becomes a fascinating and complex topic when viewed from the lens of fundamental physics. We experience mass every day in the weight of objects and in the force of gravity, yet the deeper question of where mass comes from is far from trivial. The Higgs mechanism provides an elegant explanation. Particles gain mass by interacting with the Higgs field, a process that is central to the stability of matter itself. Without the Higgs mechanism, the W and Z bosons, the particles that mediate the weak force, would have no mass, and the theory of electroweak interactions would collapse. The very stability of the universe, from atoms to galaxies, hinges on these interactions. That is why the verification of the Higgs boson was not just a technical curiosity or an academic exercise. It was a crucial step in confirming humanity's best understanding of why the universe exists in its present form. For physicists, this discovery was an affirmation that their methods, their theoretical frameworks, and the vast collaborative efforts they put into studying the universe were not in vain. They often deal with phenomena that cannot be directly observed or touched. They rely on intricate machinery, vast data sets, and layers of indirect evidence to deduce what happens on scales far too small for the human eye. The Higgs boson hunt was one of the most ambitious scientific undertakings ever attempted. It demanded energies and precision that were previously unimaginable. The Large Hadron Collider, LHC, a marvel of modern engineering and physics, stood at the heart of this mission. Constructed at a cost of billions of euros, with contributions from many countries, the LHC served as the ultimate test for the Higgs theory. The fact that the Higgs boson was discovered within its powerful collision chambers validated not only the theoretical predictions, but also the enormous collective investment in fundamental science. Yet, the story of the Higgs boson is not just about theoretical physics. It also carries profound technological implications. The development of the LHC and its advanced detectors required unprecedented innovation in multiple fields. From the creation of superconducting magnets capable of withstanding immense forces to the design of data processing algorithms that could handle petabytes of information, the technological challenges were immense. These innovations did not remain confined to the world of particle physics. The technologies developed for the LHC have found applications in fields such as medical imaging, material science, and computing. For instance, the advances made in processing large data sets at high speeds helped to fuel the rapid growth of big data analytics, an area that now plays a pivotal role in industries ranging from healthcare to finance. The LHC's success story is a testament to the idea that investing in big science can yield far-reaching benefits, not just in knowledge, but in practical technologies that impact everyday life. On a societal level, the discovery of the Higgs boson captivated the public's imagination. While fundamental physics is often relegated to niche scientific circles, the Higgs boson, sometimes referred to as the God particle, broke through into mainstream media. Though many physicists objected to the dramatic nickname, it nevertheless served to highlight the awe-inspiring nature of this discovery and the sense of wonder that accompanies uncovering the universe's most basic truths. People who might not normally follow scientific developments were drawn into the story, and many were inspired to learn more about particle physics or pursue careers in related fields. Science outreach programs and educational initiatives seized on the Higgs discovery as a perfect example of how curiosity, collaboration, and persistence can lead to world-changing breakthroughs. Beyond its scientific and technological significance, the discovery of the Higgs boson also carries profound philosophical implications. It offers direct evidence that the vacuum of space is not truly empty, but is instead filled with a field that interacts with particles to enable the very existence of atoms, chemistry, and life itself. For those who ponder the fundamental nature of existence, the discovery of the Higgs boson is a reminder that the universe is structured in ways that may be far more intricate and interconnected than we realize. While the discovery did not answer the ultimate question of why the Higgs field has the properties it does, it demonstrated that humanity's theoretical predictions about the deepest structures of the universe could indeed be verified through careful experimentation and observation. Finally, the discovery of the Higgs boson opened the door to future research in a way that few scientific breakthroughs can. While it completed the Standard Model by confirming the last missing particle, it also raised new questions about what lies beyond. The mysteries of dark matter, dark energy, and the imbalance between matter and antimatter in the universe remain unsolved. The Higgs boson's discovery may serve as a springboard for new theories and experiments that attempt to address these enigmatic phenomena. In some ways, the discovery of the Higgs boson acted as a guidepost, showing physicists what the universe is made of, and yet, at the same time, it revealed just how much more there is still to uncover. Despite its behavior largely conforming to expectations, the Higgs boson may yet hold secrets that we are only beginning to understand, leaving open the tantalizing possibility that there is far more to the universe than meets the eye. The discovery of the Higgs boson stands as a monumental testament to the power of international collaboration in the pursuit of knowledge. It wasn't simply a European achievement. CERN, where the discovery was made, is a global institution, drawing together the brightest minds from all corners of the Earth. Researchers and engineers from countries across the world contributed to this project, pooling their resources and expertise to create the world's most powerful particle collider. This global partnership was essential in constructing the Large Hadron Collider, LHC, an instrument capable of smashing protons together at unprecedented speeds, and it was that same collaborative effort that enabled the most significant scientific breakthrough of the century. In a world where many of today's challenges require nations to set aside differences and work together, the success of the LHC and the discovery of the Higgs boson are a shining example of what can be achieved when borders are transcended in the name of knowledge. The collaboration at CERN demonstrated that when countries unite with a shared focus on scientific progress, the collective achievement can be extraordinary. This wasn't merely about discovering a particle. It was about the strength of global cooperation and the ways in which humanity can come together to answer the fundamental questions of our existence. The discovery of the Higgs boson, a theoretical particle that had been predicted for nearly 50 years, showed the world that great scientific breakthroughs are possible when nations come together in unity. It was a powerful reminder of what we can accomplish when we transcend geopolitical divides and focus on the bigger picture. Moreover, the Higgs boson discovery was not just a triumph of international cooperation. It was also a reaffirmation of the methodology behind modern particle physics. Large-scale experiments are expensive, often running into billions of dollars, and many skeptics have questioned the validity of such investments. The discovery of the Higgs boson provided a strong argument in favor of these high-stakes endeavors, proving that fundamental questions about the nature of the universe can indeed be answered if society is willing to make the necessary financial and intellectual commitments. The scale and expense of the LHC may have seemed daunting, but in hindsight, it was the kind of investment that will shape scientific understanding for generations. This dynamic is akin to the spirit of space exploration. While immediate economic returns might not always be clear, the intellectual and technological dividends are undeniable. The search for the Higgs boson was a perfect example of how cutting-edge research can yield profound insights that extend far beyond the laboratory, providing benefits to society at large in ways that are often impossible to predict. The impact of the Higgs boson discovery was also felt within the scientific community itself. Particle physics is often a competitive field, with various teams racing to interpret data and develop new theories. But the discovery of the Higgs boson was different. It was a testament to the power of collaboration. The two main experiments at CERN, ATLAS and CMS, operated separately, each verifying the other's results. Yet, both were crucial in confirming the existence of the Higgs. This collaboration between theory and experiment coupled with mutual respect among the diverse teams involved, demonstrated that science moves forward most effectively when information is shared freely and when individual achievements are celebrated as part of a collective endeavor. What made the discovery of the Higgs boson so engaging was the fact that it provided a clear, definitive answer to a question that had plagued scientists for decades. Does the Higgs boson exist? Unlike many scientific inquiries that meander along uncertain paths, the search for the Higgs had a specific goal. Researchers knew exactly what they were looking for. They developed strategies to test the hypothesis by colliding protons at immense energies, and when the results came in, they provided a crystal clear resolution. This kind of definitive outcome is rare in science, where many questions linger for years without concrete answers. The public, as well as the scientific community, found this resolution profoundly satisfying, an answer to a question that had been unresolved for nearly 50 years. On a deeper level, the Higgs boson discovery underscored humanity's capacity to push the boundaries of what we know. Particle physics deals with concepts that are far removed from everyday experience. The energies involved, the timescales, and the distances explored are all beyond our daily reality. Yet scientists designed experiments to explore these extremes, shedding light on conditions that existed mere fractions of a second after the Big Bang. What they found confirmed long-standing theories about how the universe functioned in those early moments of existence. The discovery of the Higgs boson tied the present to the ancient past, linking our current understanding of the universe with the cosmic origins that shaped it. Some may argue that the discovery of the Higgs boson was inevitable, given the trajectory of scientific progress and technology. However, inevitability does not diminish the significance of the moment. Just as the moon landing was an expected outcome of the Apollo program, but still a landmark event in human history, the discovery of the Higgs was an anticipated but nonetheless monumental achievement. It marked a key moment in the journey from hypothesis to reality. July 4th, 2012, the day the discovery was announced, became one of those rare moments in scientific history when speculation and theory finally gave way to fact. It was a shift from what was once a hypothesis, a theoretical idea, to something tangible, something measurable. This moment of confirmation was not just a victory for scientists, but a reminder of what humanity can achieve with perseverance, collaboration, and curiosity. The announcement of the Higgs boson also sparked new excitement and wonder about what might come next. In the wake of such a significant breakthrough, questions emerged about what other mysteries the LHC might reveal. Could it be that dark matter, the mysterious substance that accounts for much of the universe's mass, but has never been directly observed, might one day be detected? Might the data from the LHC or future colliders reveal evidence of supersymmetric particles or open the door to new realms of physics that we have yet to imagine? The discovery of the Higgs boson was not an endpoint. Rather, it was the beginning of new avenues of exploration. It was a reminder that there are still many more secrets waiting to be uncovered, and that with the right tools and the right global support, remarkable discoveries are possible. At its core, the discovery of the Higgs boson is a celebration of human intellect and ingenuity. Theorists in the 1960s, using nothing but mathematics and physical reasoning, predicted the existence of a field that would account for particle masses, and they speculated that a corresponding boson would one day be found. Decades later, after years of theoretical work, cutting-edge technology, and global collaboration, the Higgs boson was discovered in exactly the place that theory had predicted. This triumph of the scientific method, this blend of abstract reasoning and experimental verification, is a testament to the power of human thought and the pursuit of understanding. It shows that even the most abstract and far-reaching predictions can be confirmed, so long as they are grounded in solid theoretical foundations. The impact of the Higgs boson discovery extends far beyond the walls of CERN. It is not merely another entry in the catalog of elementary particles. It is the cornerstone of the mechanism that makes the standard model of particle physics coherent. It validates a decades-long global effort, demonstrating the power of collaboration, and it opens new doors to further research. It has the potential to inspire a new generation of scientists, educators, and thinkers, while also sparking profound philosophical questions about the very structure of the cosmos. The Higgs boson discovery will undoubtedly remain one of the most significant moments in the scientific history of the 21st century, shaping both the future of physics and the broader cultural understanding of how reality can be deciphered. The announcement of the Higgs boson in 2012 was a culmination of years of hard work, speculation, and hope. For nearly 50 years, it had been the most elusive particle in the Standard Model, the last piece of the puzzle that made the theory feel incomplete. And then, in a single moment, it was no longer just a theory. It was real. It had been observed, measured, and photographed in the data collected from the world's largest scientific instrument. This discovery represents a defining chapter in the ongoing story of humanity's quest to understand the universe. And as new mysteries continue to unfold, it serves as a powerful reminder of our collective potential to unravel the deepest questions about the nature of reality. The Higgs boson may have been elusive for decades, but now it is a solid, undeniable part of our understanding of the universe. And that is a victory not only for science, but for human progress as a whole. Physicists, fresh from their monumental discovery, found themselves returning to the collision data again and again, carefully scrutinizing each event in order to verify every last detail about the newfound particle, the Higgs boson. Their task was clear yet complex: to confirm its properties, including the spin, parity, and the various channels through which it decayed. The Standard Model, a framework that had guided particle physics for decades, provided clear predictions about how often the Higgs should appear in these experiments, as well as how it should decay into other particles. These decay channels were crucial, offering measurable clues that could either validate or challenge the established theory. If the real data neatly aligned with the theoretical predictions, there was a sense of comfort in knowing that the Standard Model, at least for the moment, was correct. However, if the data presented unexpected twists, such as the appearance of extra decay modes, it could suggest the possibility of new physics beyond the Standard Model, opening the door to deeper mysteries of the universe. The weeks and months following the discovery were thus marked by intense focus on the data, rather than the initial celebratory atmosphere. While the world outside the scientific community buzzed with excitement, the physicists turned their attention to meticulously combing through massive datasets collected over numerous experimental runs to confirm and refine their findings. Outside of the scientific world, the public's reaction was varied. Some were thrilled by the discovery, given that the Higgs boson had received widespread media coverage, often being sensationalized as the God particle. Others, however, remained confused about what the discovery truly meant. The name itself sparked a layer of misunderstanding, with many conflating the Higgs boson with grand explanations of creation or cosmic significance. Physicists, both in research and outreach, found themselves working to clarify that the particle did not prove or disprove any spiritual or philosophical notions. Instead, it was a confirmation of a theoretical framework, the Standard Model, that had been guiding particle physics for decades. Despite these efforts, the public fascination with the Higgs boson was undeniable, and from a public relations standpoint, the buzz surrounding its discovery was enormous. Documentaries, science specials on television, and popular science articles began to flood the media, giving the Higgs boson a place in mainstream culture that few other subatomic particles had ever achieved. This newfound visibility also translated into more data collection, as researchers focused on refining their measurements. Their goal was not merely to prove that a Higgs-like particle existed, but to verify that it had the exact characteristics predicted by the Standard Model. Among the most critical measurements was the mass of the particle, which experiments pinpointed at around 125 giga-electron-volts, GeV. Another key characteristic was the Higgs boson spin, or rather, its lack of spin. The Standard Model predicted that the Higgs was a scalar particle, meaning it had no intrinsic spin and exhibited certain symmetry properties. Demonstrating that the Higgs boson indeed had spin 0, rather than spin 2 or some other value, was crucial to confirming that this was the particle predicted by the theory, and not an unexpected imposter. The process was far from simple. Teams designing new analyses worked closely with theoretical experts to ensure that every statistical method was double-checked and cross-referenced. Meanwhile, the Large Hadron Collider, LHC itself, began using the early results from these experiments to plan for improvements and upgrades. After the initial discovery period, the LHC underwent a scheduled shutdown, allowing engineers to enhance the collider's systems and prepare for collisions at even higher energies. This was a significant step, as higher energy collisions could produce more Higgs bosons and other rare processes, offering researchers a greater opportunity to probe uncharted territories of physics. Even as the discovery was still fresh, physicists were already looking ahead. The next phase of research would focus on understanding whether the Higgs boson could provide insights into some of the most profound unsolved mysteries in physics, including dark matter, neutrino masses, or other phenomena not explained by the Standard Model. Hopes were high, but tempered by the understanding that collider experiments are notoriously difficult, and new discoveries rarely come easily. Public interest, however, presented an opportunity for expanded science education and outreach. Museums, science centers, and institutions around the world hosted exhibitions explaining particle physics and the significance of the Higgs field, reaching out to people who might never have otherwise taken an interest in subatomic science. Through these initiatives, science communicators seized the opportunity to show how curiosity-driven research not only leads to groundbreaking discoveries, but also brings about technological innovations that impact everyday life. Yet, alongside the wave of enthusiasm, there was also skepticism. The enormous cost of conducting large-scale experiments like those at the LHC, combined with the abstract nature of the results, led some members of the public to question whether the time, money, and resources could be better spent on more immediately practical issues. Researchers found themselves defending the intrinsic value of exploring the fundamental laws of physics, arguing that breakthroughs in understanding the universe often come with unexpected benefits down the road. Within the scientific community, the post-discovery phase shifted from merely proving the existence of the Higgs boson to understanding its precise dynamics. Graduate students took on fresh projects to analyze specific decay modes, while postdocs developed new software to filter out background noise more effectively. Senior scientists proposed new theoretical frameworks, either to confirm the Standard Model's interpretation or to explore alternative possibilities. Every conference after the discovery felt like a victory lap, but with it came a sense of tension as new, unanswered questions lingered in the air. The general feeling among the scientific community was that a major piece of the puzzle had been found, yet the puzzle itself was far from complete. As time passed, experimental results began to show that the observed boson behaved much like the Higgs boson predicted by the Standard Model. The measured interactions, such as the particles' stronger coupling to heavier particles than to lighter ones, closely matched theoretical predictions. For those who had spent their careers refining the Standard Model, this consistency was thrilling. Yet, it was also somewhat unsettling for those who had hoped the discovery of the Higgs boson would provide a window into new realms of physics, such as supersymmetry or hidden dimensions. If the particle turned out to be exactly what the textbook described, it might mean fewer cracks in the Standard Model left to explore. Nonetheless, no one in the scientific community was disappointed to the point of dismissing the significance of the discovery. After all, confirming the accuracy of the Standard Model's predictions was itself a remarkable achievement. In the years that followed, more subtle measurements began to emerge, further bolstering confidence that the particle detected at 125 GeV was indeed the Higgs boson predicted by the theory. The LHC's second run and subsequent runs provided even more collision data at higher energies, improving the statistical precision of the measurements. Collaborative teams from the CMS and ATLAS experiments, the two general-purpose experiments that had first spotted the Higgs, shared their findings, ensuring consistency and combining results when beneficial. While minor anomalies occasionally surfaced, they typically dissipated as more data was gathered or were explained by known effects. This iterative process highlighted the meticulous nature of particle physics, where every claim is rigorously tested before drawing definitive conclusions. Looking at the broader horizon, theorists began discussing the potential implications of the confirmed Higgs boson. Some saw it as a key to unlocking a deeper understanding of the universe's structure, while others argued it marked the end of certain speculative theories that had not predicted a Higgs boson at the discovered energy. While the public may have expected immediate technological breakthroughs or sudden revelations about the cosmos, the reality was more measured. The discovery of the Higgs boson, even one as significant as this, was merely a part of a much longer arc of research. The initial excitement eventually gave way to the steady pace of scientific work, where incremental gains are often celebrated in more specialized circles. In hindsight, the period following the discovery of the Higgs boson was marked by both celebration and recalibration. Researchers were thrilled to have found the Standard Model's long-sought missing piece, but they remained cautious about declaring any grand unification of theories. There were still many unanswered questions, including the mysteries of dark matter, dark energy, and the hierarchy problem. The discovery of the Higgs boson answered a critical question: how fundamental particles acquire mass without violating the underlying symmetries of the Standard Model. Yet, this solution did not close every door. Rather, it created a foundation upon which more confident, targeted questions could be asked. In the years that followed, the scientific community came to recognize that the next steps in exploring the fundamental fabric of the universe might demand new approaches, perhaps larger colliders or entirely different experimental techniques. One major milestone had been achieved, but many more awaited on the horizon. Throughout this entire journey, the term God particle continued to stir debate. While many physicists found the label to be a persistent annoyance, seeing it as a sensationalized and misleading misrepresentation of their work, it had taken on a life of its own, largely due to media coverage and promotional choices. Some saw it as a marketing gimmick, while others believed it had successfully captured the public's imagination, making particle physics more accessible and engaging to a wider audience. However, this nickname, with its religious and mystical connotations, often clashed with the true nature of the Higgs boson, a particle best understood through the lens of quantum field theory and the mechanics of particle interactions. Despite its controversial origins and implications, the label God particle had served to generate interest in a field that was previously obscure to most of the public, helping to spark curiosity about the fundamental workings of the universe. However, with this discovery came a wave of intrigue, closely followed by confusion. The term God particle rapidly spread, but with it many misconceptions arose, as many assumed that the term had theological or mythological connotations, perhaps suggesting a connection to creation stories or existential debates about the origin of the universe. Scientists, eager to clarify, frequently addressed the misunderstanding in interviews and public lectures, emphasizing that God particle was merely a catchy nickname, one without deep theological implications or significance. Despite their best efforts, however, the mainstream media seemed slow to absorb this clarification. The term continued to surface in articles, broadcasts, and online discussions, often with little nuance or context. News outlets, driven by the allure of catchy headlines, continued to use the term to attract viewers or readers, knowing full well that sensational language tends to increase engagement. As a result, the Higgs boson's association with this loaded label became increasingly entangled with misconceptions, obscuring the particle's true scientific nature. This cycle of confusion was perpetuated by the media's insistence on using the phrase, even when press releases from institutions like CERN explicitly tried to avoid it. Editors, aware that controversial or eye-catching terms tend to draw larger audiences, would sometimes sneak it back into their stories, prioritizing clicks over accuracy. The unintended consequence was that the Higgs boson's identity remained shackled to a term that was never meant to endure. However, in an ironic twist, this very confusion may have spurred public interest. The intrigue surrounding the God particle prompted many curious individuals to delve deeper into the science behind the discovery. This journey often led to an understanding of the Higgs field, the mechanism through which particles acquire mass, a concept that had previously been abstract and esoteric to most. In a sense, one could argue that any publicity, even that which arises from misunderstanding, could be beneficial if it sparks an educational journey. Outreach programs aware of the God particle phenomenon seize the opportunity to host talks and lectures that use the term as a gateway, offering audiences an accessible entry point into the complex world of particle physics. For some scientists, this approach was uncomfortable. Sensationalizing science for the sake of public interest seemed at odds with the careful, precise language of academic discourse. Yet others saw it as a practical tool, a way to draw people in, to fill lecture halls and spark curiosity. Once there, they could guide them toward a more accurate and comprehensive understanding of the Higgs mechanism, gauge symmetry, and spontaneous symmetry breaking. From a historical perspective, physics has often been home to sensational labels and oversimplified concepts. Quantum mechanics, for instance, has been described as weird and spooky, especially in reference to phenomena like entanglement, while black holes, once confined to the realm of theoretical curiosity, have captured the public's imagination as mysterious and almost mythical cosmic objects. The God particle label, then, is not entirely unique in the annals of scientific branding. It belongs to a broader tradition of catchy, though often oversimplified, terms that help introduce complex subjects to a wider audience. While this branding strategy can be effective in generating public interest, it also brings with it the risk of misinterpretation, overshadowing the nuanced, intricate realities of the science it represents. Nevertheless, the God particle moniker remains an indelible part of the public narrative surrounding the Higgs boson discovery. It serves as a cultural artifact, an example of how the intersection of science, communication, and public perception can result in both positive and negative consequences. The problem arises when such branding begins to obscure the essence of the scientific breakthrough, focusing the public's attention on one specific aspect of the Standard Model while neglecting the broader context in which the Higgs boson resides. While undeniably significant, the Higgs boson is but one part of a much larger interconnected framework of particles and forces that govern the universe. The God particle label, by elevating it above the other components of the Standard Model, risks perpetuating the misconception that the Higgs is the pinnacle of subatomic phenomena, relegating other particles like quarks, leptons, and gauge bosons to a secondary role. In the years since the discovery, the God particle nickname has become so entrenched in the popular narrative that it is unlikely to disappear anytime soon. It still appears in headlines, documentaries, and casual conversations, and while it may frustrate physicists, it also serves as a reminder of how pop culture can shape the public's perception of science. Some scientists, acknowledging the deep-seated nature of the term, have come to accept it, though they continue to stress the importance of accurate scientific communication. Public lectures, articles, and documentaries often begin by nodding to the nickname, acknowledging its place in popular culture, before transitioning into a thorough explanation of the true scientific significance of the Higgs mechanism. This approach recognizes the inevitability of the term's continued use, while also offering an opportunity to address the misconceptions that accompany it. In casual conversation, even some researchers have been known to refer to the Higgs boson as the God particle, doing so with a sense of irony, fully aware of the term's imprecise nature. This has led to a wider debate about whether such labels are ultimately detrimental to scientific literacy. Some educators argue that the God particle is a useful entry point, a term that sparks curiosity and leads to deeper exploration of fundamental physics. Others, however, caution that it sets up unrealistic expectations, particularly in regards to the supposed divine or all-encompassing nature of the Higgs boson. It can also obscure the collaborative nature of scientific discovery, focusing too narrowly on one particle and ignoring the complex network of interactions that define the Standard Model. While the Higgs boson is undoubtedly an important piece of the puzzle, it is not the only foundational component of modern physics. The entire array of particles and forces, the quarks, the leptons, the gauge bosons, and the intricate relationships between them, are equally deserving of recognition. By elevating the Higgs boson to the status of a God particle, There is a risk of creating a hierarchy in which this one discovery is seen as the zenith of particle physics, to the detriment of the broader and equally fascinating world of quantum mechanics. Despite these concerns, the nickname persists in the public consciousness, shaping the way the Higgs boson is perceived and discussed. It has become an enduring part of the narrative surrounding one of the most significant discoveries in modern science. The excitement and controversy surrounding the Higgs boson's discovery sparked debates not only among physicists, but also among religious scholars and curious members of the public. The term God particle, for all its flaws and frustrations, has acted as a bridge between the scientific community and the wider world. It has helped to spark interest in a topic that might otherwise have remained obscure and abstract, leading more people to explore the intricacies of particle physics and the fundamental workings of the universe. In the end, the God particle label may never be fully embraced or retired, but it will always serve as a reminder of how science, communication, and public perception intersect. A single phrase, catchy though it may be, can shape how a scientific discovery is understood by the public, for better or for worse. As the world continues to grapple with the implications of the Higgs boson's discovery, the term stands as a testament to the complexities of scientific communication, the challenges of bridging the gap between expert knowledge and popular understanding, and the ways in which the language of science can evolve and sometimes be distorted through the filter of public fascination. The announcement of the Higgs boson discovery in 2012 marked a pivotal moment in the history of physics, setting the stage for what would become one of the most anticipated Nobel Prizes in recent memory. For decades, scientists had sought the elusive particle, with the theoretical groundwork laid as early as the 1960s, when Peter Higgs, Francois Englert, and others published their groundbreaking papers on the mechanism that would later bear their name. The Higgs mechanism, which explained how particles acquire mass, was hailed as a brilliant solution to one of the most vexing problems in the standard model of particle physics. But it wasn't until the Large Hadron Collider, LHC, experiments in 2012 that the search for the Higgs boson finally bore fruit. Once the discovery was confirmed, attention swiftly turned to the Nobel Committee, with the scientific community eagerly awaiting the announcement of the Nobel laureates. The Nobel Prize in Physics for 2013 was awarded to Peter Higgs and Francois Englert for their theoretical predictions, which had suggested the existence of a mass-giving particle. The award was a fitting tribute to the groundbreaking work of the two scientists, and it was met with widespread acclaim in the physics community. Yet, as is often the case with such prestigious honors, it also sparked debate over who was included and who was left out. Despite the recognition of Higgs and Englert, the Nobel Prize's failure to acknowledge some of the other key figures involved in the theoretical development of the Higgs mechanism, such as Robert Brout and others, left some members of the scientific community questioning the committee's decisions. The Nobel Prize in Physics, while revered as one of the highest honors in science, operates under constraints that often do not reflect the collaborative nature of modern scientific breakthroughs. With a cap of 3 individuals per award, this limitation has at times led to the exclusion of critical contributors to groundbreaking discoveries. The case of the Higgs boson discovery is a prime example. Robert Boot, who had worked closely with Peter Higgs and Francois Englert, passed away before the prize was announced. This omission drew considerable attention to the fact that other key figures, Gerald Guralnick, Carl Hagen, and Tom Kibble, had also independently published papers around the same time, addressing similar theoretical questions regarding the Higgs mechanism. While their work was acknowledged within the academic community, the Nobel Committee chose not to expand the award beyond Higgs and Englert. This sparked debate. Why were these contributions not more visibly recognized? But as the Nobel rules clearly state, only a select number of people can share the prize, and the committee often adheres to a traditional interpretation of which contributions are deemed the most seminal or foundational. Despite the controversy, the atmosphere during the Nobel announcement was one of celebration. Peter Higgs, in particular, had lived a relatively quiet life, preferring to avoid the limelight. Known for his reluctance to engage with the media, he had frequently expressed how overwhelming the attention felt. Even as the world associated his name with the discovery of the boson, Higgs remained steadfast in his belief that the achievement was not his alone. He was quick to emphasize the collective effort of thousands of scientists and engineers at CERN, whose work in creating the experimental environment was as essential to the discovery as his theoretical framework. At the award ceremony, Higgs gave humble remarks, reiterating that the breakthrough was a product of the scientific community as a whole. Englert likewise used his moment in the spotlight to stress the teamwork involved, while also reflecting on the historical context of their work. Together, they had developed a theory that proposed a mechanism by which mass could arise without violating gauge invariance. But it took nearly 50 years of tireless work, led by experimentalists and bolstered by the construction of one of the most complex machines in history, to verify that theory. The Nobel Prize served to refocus global attention on the collaborative nature of discoveries in particle physics. The scale of modern experiments like the ATLAS and CMS collaborations, which were central to the detection of the Higgs boson, is staggering. These massive efforts involve thousands of scientists, technicians, and support staff, all working together in a highly coordinated fashion. The decision to award the prize to only 2 individuals prompted some to question whether the Nobel format was outdated for the age of big science. Critics argued that entire collaborations should be recognized, or that the prize criteria should be more flexible. On the other hand, defenders of the tradition maintained that awarding the Nobel to key figures preserved its prestigious aura, highlighting the importance of groundbreaking theoretical contributions that lay the foundation for experimental confirmation. Another aspect of the Nobel story that deserves attention is its timing. The Nobel Committee typically waits for definitive experimental confirmation before awarding the prize. In the case of the Higgs boson, this confirmation took decades to achieve, largely due to the immense financial and technological challenges involved in building equipment capable of detecting the particle. The discovery itself was a triumph not just of intellectual insight, but of patience and perseverance. Those who had worked on the Higgs mechanism had always believed that the particle would eventually be found, but the scale of the experimental effort required to prove it demanded a near superhuman effort from the physics community. When the discovery was finally announced, it seemed almost inevitable that a Nobel Prize would follow, but not without rigorous review of the data and the theory's significance. Outside the academic world, the announcement of the Nobel Prize reignited public interest in physics. Mainstream media outlets once again turned their focus to the Higgs boson, discussing its significance for our understanding of mass and fundamental forces. Schools, universities, and even informal science clubs organized events, discussions, and viewing parties to celebrate the moment. Physics had captured the public's imagination in a way that only a few discoveries in science ever managed to do, joining the ranks of other groundbreaking achievements that transcend the confines of academia. For many, even those with only a vague understanding of the Higgs boson, the news prompted a deeper curiosity about the nature of mass and the fundamental forces that govern the universe. For Peter Higgs and Francois Englert, the recognition marked a profound shift in their personal and professional lives. They became public figures in a way that few theoretical physicists ever experience. Interview requests poured in, and academic institutions around the world extended invitations for lectures and honorary degrees. While both had long been recognized within the scientific community, the Nobel Prize brought them an additional layer of prestige and media attention. The announcement represented in some ways the completion of a journey that had begun with a hypothesis and ended with the confirmation of a fundamental piece of the universe's puzzle. Yet, despite the overwhelming recognition, both men remained humble, consistently downplaying the idea that they were the sole architects of the discovery. They were quick to redirect credit to the larger scientific community, those who had advanced, tested, refined, and ultimately confirmed the theory. However, the controversy surrounding the Nobel Prize's selection process didn't end with the announcement. Some critics continued to voice strong objections to the omission of Guralnick, Hagen, and Kibble. Their independent work had closely aligned with that of Higgs and Englert, and many believed they deserved a direct share of the Nobel recognition. Some suggested that the Nobel Committee might have delayed the award for a year to better account for the contributions of these theorists. But the Nobel Committee is notoriously reluctant to revisit its decisions, and the awarding of the prize to Higgs and Englert was largely considered final. Within the scientific community, it is often noted that Guralnick, Hagen, and Kibble did receive prestigious honors for their work, such as the Sakurai Prize, which acknowledged their significant contributions to the field. Still, the Nobel Prize holds a unique place in both public perception and the scientific tradition. It is the most coveted and, consequently, the most debated honor when there are questions about who should be recognized. Finally, a crucial dimension of the Nobel narrative lies in its focus on discovery and invention, often at the expense of recognizing the equally important experimental efforts that bring theory to life. In the case of the Higgs boson, the experimental side of the discovery was immense. The ATLAS and CMS collaborations worked tirelessly to detect the Higgs by analyzing billions of proton collisions, requiring a collective effort of unprecedented scale. While the Nobel Prize has historically focused on the theoretical, the massive scale of modern experimental efforts has raised questions about whether the prize should expand its scope to include these large-scale collaborations. However, the process through which the Nobel Prize is awarded, with its limitations and constraints, makes it nearly impossible to honor the thousands of scientists whose contributions led to groundbreaking discoveries. Despite this, the collaborations that gave birth to major advances, such as those leading to the Higgs boson discovery, have not gone unnoticed. Many of the scientists involved in these monumental experiments received other prestigious awards from various scientific institutions. Yet for some, this situation highlighted the inadequacies of a system that was conceived in an era when major scientific breakthroughs typically emerged from small teams, or, in rare cases, lone scientists working in isolation. As science grew larger and more collaborative, it became increasingly apparent that the old methods of recognition could no longer keep pace with the scale of modern research. The discovery of the Higgs boson, confirmed after decades of unrelenting effort, was emblematic of the new age of big science. This era demands new forms of acknowledgement, a shift away from individual recognition toward a more collective model. The Nobel Prize ceremony itself served as a symbolic capstone for this achievement, an acknowledgement that the Higgs mechanism, once a bold idea proposed in the 1960s, had evolved from an unproven hypothesis to a well-validated piece of scientific reality. It was a moment in history that underscored the transformation of theory into accepted fact, marking a triumph not just for the theorists, but for the thousands of researchers across the world who contributed to this success. The golden medal handed out that day symbolized not only the brilliance of Peter Higgs and Francois Englert, but also the collective achievement of the scientific community that had made this discovery possible. It was a recognition of the method that blended bold theoretical insight, cutting-edge technology, and large-scale international collaboration. For a new generation of physicists, the announcement of the Nobel Prize acted as a beacon of both inspiration and caution. It showed that scientific progress, especially in the realm of fundamental research, requires more than just intellectual brilliance. It demands immense patience, persistence, and often years or even decades of uncertainty. Engaging in this type of research is not for those seeking instant gratification or quick rewards. Instead, it requires a steadfast commitment to the long road of discovery, a willingness to explore the unknown with no guarantee of success. Yet, when the breakthroughs do come, they have the potential to completely reshape our understanding of the universe. In this sense, the recognition of the Higgs boson was more than just a personal victory for its discoverers. It was a testament to the power of perseverance and intellectual daring, to the relentless pursuit of knowledge against the odds. The Higgs boson itself answered one of the most fundamental questions in physics: how do particles acquire mass? But despite the monumental nature of this discovery, it also exposed the vast gaps in our understanding of the universe. The confirmation of the Higgs boson did not instantly resolve the biggest mysteries in modern science. Instead, it opened the door to even more profound questions, leaving the physics community eager for further answers. Many had hoped that the detection of the Higgs boson would provide a key to unlocking the mysteries of dark matter, the imbalance between matter and antimatter, and many other unanswered questions that have long haunted scientists. However, this discovery did not deliver the kind of immediate, sweeping answers many had hoped for. Instead, it reaffirmed the limitations of the standard model of particle physics, showing that even with this crucial piece added to the puzzle, there remain vast areas of unexplained phenomena. One of the most pressing mysteries that remains unsolved is the nature of dark matter. Observations of galaxies have shown that they rotate in ways that cannot be explained by the gravitational effects of the visible matter alone. This led scientists to hypothesize the existence of an invisible form of mass, known as dark matter, which must be exerting a gravitational pull. However, despite numerous experiments aimed at detecting a particle responsible for dark matter, no conclusive evidence has been found. The discovery of the Higgs boson did not provide any clues that could lead to the identification of dark matter. Neither did it uncover any hidden forces that might link the Higgs field to an undiscovered sector of physics that could explain dark matter. Researchers had hoped that studying the decays of the Higgs boson would reveal new exotic particles or invisible decay channels that might offer some insight into dark matter. But the data so far has shown no significant deviations from the predictions made by the standard model, leaving the mystery of dark matter as elusive as ever. Gravity, another one of the great unsolved puzzles of physics, also remains largely unaffected by the discovery of the Higgs boson. The standard model successfully describes the electromagnetic, weak and strong nuclear forces, but gravity is best understood through Einstein's theory of general relativity, which treats gravity as the curvature of space-time. Efforts to unify general relativity with quantum field theory have so far yielded no single universally accepted framework. The discovery of the Higgs boson did not bring us any closer to a unified theory of quantum gravity. While the Higgs field is responsible for giving mass to particles like the W and Z bosons, it does not provide any insight into how mass might relate to the curvature of spacetime at the quantum level, particularly at the Planck scale. Neutrinos, the elusive and mysterious particles that are incredibly difficult to detect, also remain an enigma. For years, the standard model assumed neutrinos were massless, but experiments studying neutrino oscillations, where neutrinos change from one type to another, have shown that they must possess a small, non-zero mass. The simplest form of the Higgs mechanism does not provide a mechanism for giving neutrinos their mass unless additional components are introduced into the theory. Some theorists have proposed the existence of a seesaw mechanism, which could explain the small masses of neutrinos, but testing this idea experimentally remains a major challenge. One of the most perplexing issues that has yet to be addressed by the Higgs boson discovery is the matter-antimatter imbalance in the universe. According to observations, matter vastly outweighs antimatter in the observable universe. This is strange because the Big Bang should have produced equal amounts of both. If there had been perfect symmetry, matter and antimatter would have annihilated each other upon contact, leaving almost nothing behind. The fact that matter dominates suggests that some process tipped the balance in favor of matter. Some scientists believe that the Higgs field may have played a role in this asymmetry, particularly during the electroweak phase transition. However, the standard model, in its simplest form, does not produce a strong enough phase transition to explain this imbalance. As such, the discovery of the Higgs boson did not provide a definitive answer to this fundamental question. The hierarchy problem, another major issue left unresolved by the discovery of the Higgs boson, concerns the vast difference in strength between the gravitational force and the other fundamental forces. Theoretically, the mass of the Higgs boson should be much larger, given the strength of the gravitational force, but this is not the case. While some proposed theories, such as supersymmetry, may offer a solution, the Higgs boson itself does not directly address this problem. In many ways, the discovery of the Higgs boson, while monumental, serves as a reminder of the vast unknowns that remain in the realm of physics. It marked a critical achievement, but it also revealed that there is much more to explore, much more to understand. The Higgs boson provided answers to some of the most fundamental questions in particle physics, but it also opened the door to new, more profound questions that scientists will continue to grapple with for years, if not decades, to come. The Higgs boson, with its mass hovering around 125 giga-electron-volts, GeV, presents an intriguing puzzle within the realm of particle physics. Although this mass value is seemingly modest compared to the Planck scale, a fundamental threshold associated with gravity, its implications are far from trivial. Quantum corrections, which are expected to push the Higgs mass to far higher values, should be countered by a specific mechanism that cancels out these effects. Yet, the Standard Model offers no natural explanation for why the Higgs mass is so surprisingly low. In theory, the Higgs mass should be much greater, yet it remains constrained, leading many to speculate about the presence of new physics beyond the known framework. Supersymmetry, extra dimensions, or other novel principles might offer an explanation for this fine-tuning, but until now, experimental evidence for these hypotheses remains elusive. The measurement of the Higgs boson's mass has only served to deepen the mystery of why nature has chosen such a delicate balance. While this discovery solidified our understanding that the Higgs field is responsible for giving particles mass, it raised even more questions. One of the most persistent challenges concerns the mass hierarchy of fundamental particles. The Higgs field couples to fermions, setting their masses, yet it provides no insight into why there is such a vast disparity between the masses of particles like the top quark, extremely heavy compared to the up quark, or why the electron is so light in contrast to the much heavier tau lepton. These mass patterns seem arbitrary within the Standard Model, a fact that leaves many researchers wondering if there's a deeper, as yet undiscovered principle at play. Another conundrum highlighted by the Higgs discovery is the strong CP problem. The strong force which binds quarks together within protons and neutrons should, in principle, be capable of violating charge parity CP symmetry. If this were the case, experiments would detect a permanent electric dipole moment in the neutron. However, no such dipole has been observed. While the Higgs mechanism does not explain why this violation is so minuscule, or even absent altogether, the strong CP problem remains an unsolved riddle. Moreover, the Higgs boson's properties hint at the possibility of a fragile vacuum. The measured values of both the Higgs mass and the top quark mass suggest that the vacuum of our universe might exist at a precarious tipping point, straddling the boundary between stability and instability. In theory, if the vacuum is metastable, a quantum tunneling event could send the universe into a lower energy state, leading to catastrophic consequences, though this event, if it were to happen, might be billions of years away. Despite this unsettling possibility, the discovery of the Higgs boson didn't shed light on why the vacuum is so delicately balanced, nor did it provide an explanation for the mysterious force that might stabilize it. The Higgs mechanism also fails to account for the observed acceleration of the universe's expansion. Observations of distant supernovae and the cosmic microwave background radiation suggest that this acceleration is driven by a tiny cosmological constant, or something similar. But the Standard Model, even with the inclusion of the Higgs field, doesn't produce the necessary tiny value for dark energy. In fact, naive calculations based on the Standard Model overshoot the required value by an enormous factor. The discovery of the Higgs boson, with its mass of 125 GeV, did nothing to resolve this glaring mismatch. Dark energy remains one of the biggest unsolved mysteries in cosmology, and the Higgs boson has not provided any new insights. Despite these gaps in understanding, the discovery of the Higgs boson was hailed as a milestone in physics. On one hand, it validated the concept of spontaneous electroweak symmetry breaking, a cornerstone of the Standard Model and a fundamental aspect of modern particle physics. On the other hand, it failed to deliver the anticipated breakthroughs into new realms of physics. Prior to the discovery, many hoped that finding the Higgs boson would offer direct evidence for supersymmetric particles, extra dimensions, or other exotic phenomena. However, data from the Large Hadron Collider, LHC, have not provided any immediate evidence for these ideas. The Higgs boson's production rates and decay patterns have so far matched the Standard Model's predictions, leaving little room for unexpected discoveries. Physicists remain hopeful that more precise measurements could reveal tiny deviations from the Standard Model, such as rare decays or subtle changes in the way the Higgs interacts with other particles. In fact, vast amounts of data are being analyzed in the hopes of uncovering such anomalies. Yet, despite these efforts, no such deviations have been detected so far. This ongoing search serves as a reminder that while the Higgs boson was a groundbreaking discovery, it did not provide the ultimate answers to the fundamental questions of the universe. Grand unified theories, GUTS, which seek to combine the strong, weak, and electromagnetic forces at exceedingly high energy scales, remain speculative. These theories predict additional gauge bosons or multiple Higgs fields. The observation of a single Higgs boson at the LHC neither confirms nor denies these unification scenarios. If the unification of forces occurs at an energy scale far beyond the reach of current particle colliders, the Higgs discovery may offer little direct insight into this possibility. Thus, the search for a true understanding of how the forces of nature are unified continues. Similarly, neutrino physics remains shrouded in uncertainty. Some theories suggest that neutrinos could acquire their masses through the existence of heavier neutrino partners, right-handed neutrinos, that may be present at higher energies. While the Higgs boson does not rule out this possibility, it also does not provide direct evidence for it. Detecting or ruling out the existence of right-handed neutrinos will likely require new experiments or more powerful particle colliders. But until then, the precise mechanism that gives neutrinos mass remains an open question. The mystery of the matter-antimatter imbalance in the universe also continues to perplex physicists. In the early moments of the universe, it is believed that matter and antimatter should have been created in equal amounts. However, the universe today is overwhelmingly made of matter, and the reason for this asymmetry remains unclear. Some theorists have suggested that the electroweak phase transition might have been strong enough to create this imbalance, but that would require modifications to the simplest Higgs scenario. So far, experiments have not found the need to alter the standard Higgs model to account for this asymmetry, meaning the matter-antimatter puzzle remains unresolved. These challenges underscore the fact that while the discovery of the Higgs boson filled a crucial gap in the standard model, it also highlighted the many remaining unknowns. It proved that spontaneous symmetry breaking is central to the electroweak interactions, but it did not connect all the dots. Crucial mysteries like dark matter, dark energy, neutrino masses, quantum gravity, and the matter-antimatter imbalance remain as elusive as ever. The Higgs boson has become one of the defining features of modern physics, but it is not the end of the story. Some researchers still hold out hope that deeper insights will emerge through more refined measurements or through the discovery of rare processes involving the Higgs. Additionally, new technologies or experimental methods might eventually reveal particles that interact with the Higgs in novel ways, providing fresh clues about physics beyond the standard model. Until such breakthroughs occur, however, the Higgs boson will remain the crown jewel of the standard model, confirming that mass generation occurs as predicted, but leaving many questions unanswered. In summary, while the discovery of the Higgs boson was a monumental achievement, it did not provide all the answers. It confirmed the mechanism by which particles acquire mass, but it did not solve the mysteries of dark matter, unify gravity with quantum mechanics, explain the strange pattern of fermion masses, or address the matter-antimatter imbalance. It also left unresolved issues such as vacuum stability and dark energy. Despite its importance, the Higgs boson ultimately exposed just how much of the cosmic puzzle remains unsolved. Beyond the realm of particle physics, high-energy phenomena like cosmic rays and gamma-ray bursts provide another avenue for exploration. These events can push the known laws of physics to their limits, generating collisions at energies far beyond those achievable in particle colliders. While the Higgs boson confirms that the standard model's predictions for mass generation hold true at accessible energies, it doesn't address whether new physics arises in these extreme astrophysical environments. If ultra-heavy particles or novel interactions exist at energy scales beyond the LHC's reach, the Higgs boson alone cannot reveal them. Studying cosmic events might offer new insights into the fundamental nature of the universe, but for now, the Higgs remains disconnected from these high-energy mysteries. The possibility of multiple Higgs bosons adds yet another layer of complexity. While the simplest models include just one Higgs, alternative frameworks predict the existence of additional Higgs-like particles, each with different masses or charges. If such particles exist, they could potentially help explain some of the mysteries that the single Higgs boson cannot. But until further experimental evidence emerges, the true nature of the Higgs boson and its role in the universe remains a tantalizing mystery. However, searches for additional Higgs bosons at the Large Hadron Collider, LHC, have thus far yielded no conclusive evidence. While this does not rule out their existence, it does suggest that if they do exist, they are likely either more massive than the collider's current detection capabilities can handle or interact too weakly to be easily identified. This leaves their status in a state of uncertainty, adding to the complexity of our understanding of the Higgs boson. The story, however, grows even more intricate. Once the Higgs boson was confirmed at the LHC, the scientific community faced a pivotal question. Did this discovery pave the way for uncovering new physics? Although the detection of the Higgs boson confirmed the Standard Model's mechanism for providing mass to fundamental particles, many researchers remained unconvinced that this was the full picture. The Standard Model, though elegant, leaves several key phenomena unaddressed, most notably gravity and dark matter. For this reason, many theoretical physicists sought to extend the model with additional frameworks or modifications that could explain these unexplained mysteries. A primary focus for many of these theorists was supersymmetry, or SUSY, which quickly became one of the most discussed theories. Supersymmetry proposed that every known particle would have a corresponding partner particle, known as a superpartner, which would differ in spin by half a unit. This idea would, in effect, double the number of fundamental particles in the universe. One of supersymmetry's most appealing aspects was its potential to resolve the hierarchy problem by canceling out large quantum corrections that otherwise destabilize the Higgs boson's mass. Furthermore, supersymmetry offered a potential explanation for dark matter by providing candidates like the neutralino, which could be stable and abundant in the universe. Before the Higgs boson was discovered, many hoped that once the particle was found, the corresponding superpartners would soon follow. Yet as more data poured in from the LHC, no direct evidence for these superpartners emerged at the energies accessible to the collider. This did not outright dismiss supersymmetry, but rather place constraints on the simplest or low-energy versions of the theory. In response, researchers began proposing more complex versions of supersymmetry, or suggested that these superpartners might exist at higher mass scales, beyond the current reach of the LHC's detectors. Another concept that gained attention was the idea of extra dimensions. Rooted in string theory, these theories postulated that our familiar three-dimensional space might not be the whole story. There could be additional spatial dimensions curled up at minuscule scales that are inaccessible to our everyday experience. Some models suggested that the Higgs field might reside in one of these higher dimensional spaces, providing a possible explanation for the disparity between the weak scale of the Higgs and the much stronger gravitational force observed at the Planck scale. If extra dimensions existed and were accessible, high-energy collisions might produce detectable phenomena such as microscopic black holes or Kaluza-Klein excitations, which are higher dimensional versions of standard particles. Yet, despite extensive searches, no clear signals of these phenomena have been found, making the simpler versions of these extra-dimensional models harder to support. Alongside these ideas, there were also theories proposing two Higgs doublet models. Instead of one Higgs field, these models proposed two, leading to multiple Higgs bosons, often including charged Higgs bosons and other neutral states. Such models could have significant implications for the matter-antimatter asymmetry in the universe. They could also lead to different decay patterns for the Higgs boson, which could potentially be detected at particle colliders. While searches for these additional Higgs bosons at the LHC have not yielded definitive results, the two Higgs doublet models continue to be a viable possibility, especially within supersymmetry, which naturally includes multiple Higgs fields. Another avenue of exploration was composite Higgs models. These ideas suggest that the Higgs boson is not a fundamental particle, but rather a composite object made up of more basic constituents. This concept draws an analogy to protons and neutrons, which are themselves composed of quarks bound together by the strong force. In the context of the Higgs boson, if it were a composite particle, it might help resolve the hierarchy problem in a manner similar to the dynamics of quantum chromodynamics, QCD. In such models, the Higgs mass could be stabilized without requiring delicate cancellations. While these composite Higgs models are intriguing, they typically predict resonances or other particles that should appear in collider experiments. So far, however, no definitive evidence for these predicted states has emerged, leaving the possibility open but unconfirmed. Grand unified theories, GUTS, have also stood out as overarching frameworks attempting to unify the three fundamental forces of the standard model, strong, weak, and electromagnetic, into a single force at high energies. Common GUTS involve larger gauge groups that would eventually break down into the standard model's groups as energy decreases. These theories often introduce new heavy particles and multiple Higgs fields to achieve the necessary pattern of symmetry breaking. While the discovery of the Higgs boson at 125 GeV did not provide a direct confirmation or refutation of GUTS, the continued absence of certain predicted effects has placed limits on the simpler versions of these theories. GUTS remain compelling but difficult to test directly. Another set of ideas revolved around the neutrino sector, particularly extensions involving the seesaw mechanism. In this framework, the tiny masses of neutrinos arise from mixing with very heavy right-handed neutrinos. If these heavy neutrinos exist, they might also be linked to theories of leptogenesis, which try to explain the matter-antimatter imbalance in the universe. While the Higgs field plays a crucial role in giving mass to the known neutrinos, an extended sector, including the heavy right-handed neutrinos, would be necessary to complete the full picture. However, if these heavy neutrinos are beyond the reach of current experiments, it remains difficult to confirm or refute these ideas. Another class of theories emerged with portal models, which proposed that the Higgs boson could act as a bridge to a hidden sector, one that might contain dark matter particles or other exotic states that interact with ordinary matter only via gravity or through a weak coupling to the Higgs field. If the Higgs boson occasionally decayed into these hidden particles, it might produce missing energy or unusual decay products that could be detected by LHC detectors. Researchers have combed through LHC data looking for signs of such invisible Higgs decays or displaced vertices that could point to a hidden sector, but no clear signals have yet emerged. Some theorists also explored more radical ideas, questioning the very nature of the vacuum itself and the role of the Higgs field within it. One such proposal suggested that the universe might be in a false vacuum state, which could eventually transition to a true vacuum with different physical parameters. Others speculated that the Higgs field might vary over time or space. These concepts, though difficult to test, highlight the willingness of theoretical physicists to rethink the fundamental assumptions of the Standard Model in an effort to address its unresolved questions. Finally, the concept of quantum gravity also tried to incorporate Higgs-like fields. While the Higgs boson's discovery did not directly confirm or contradict these quantum gravity theories, it did not rule them out either. One of the challenges in testing these approaches lies in the fact that quantum gravity is believed to operate at extremely high energies, well beyond the capabilities of current experimental facilities. In addition to these theoretical efforts, dark matter remained a major driving force behind many of these extensions. Whether through supersymmetry, extra dimensions, or other frameworks, many theories sought to produce stable particles that could account for the observed dark matter relic density in the universe. The properties of the Higgs boson, its mass, interactions, and decay modes, placed important constraints on how such dark matter candidates might behave. For instance, if a new particle just above half the Higgs mass existed, the Higgs boson could decay into pairs of this particle, producing missing energy, a signature that could potentially be detected by the LHC. However, no such definitive signals have been observed so far, suggesting that either this scenario is not happening or the coupling between the Higgs and such a particle is too weak to detect. Experimentally, the LHC was not the only place to search for clues. Precision measurements in flavor physics as well as rare decays of mesons were also explored for signs of new heavy particles that might loop in the background of these processes. Additionally, astrophysical and cosmological data were scrutinized for any anomalies that could hint at physics beyond the standard model. If such anomalies were confirmed, they could provide key insights into which theoretical frameworks might be true and which could be excluded. The search for new physics, driven by the enigmatic Higgs boson, continues to be a thrilling and ongoing endeavor, one that keeps pushing the boundaries of what we know about the universe. However, many of the anomalies initially discovered in particle physics turned out to be inconclusive or gradually faded into the background as more precise data emerged. This lingering uncertainty left a vast expanse for speculation, with theorists proposing a myriad of alternatives, but without the crucial experimental results needed to definitively select a clear winner. Amid this sea of possibilities, one particular idea gained increasing traction: the concept of nightmare scenarios. This term referred to the unsettling prospect that the Higgs boson might be exactly what the standard model predicts, a straightforward particle with no detectable deviations, and that any new physics could be located at energy scales far beyond the reach of current technology. In this scenario, experiments would continue to validate the standard model without revealing any new particles or forces, providing a frustratingly familiar outcome. While such a situation was less than thrilling for some, it remained entirely consistent with the results observed by the Large Hadron Collider, LHC. Despite this apparent dead end, there remained compelling reasons to continue the search for answers. Even if the Higgs did not immediately open the door to new physics, rare and elusive processes could emerge, only detectable through massive data samples or next-generation particle colliders. Future machines, such as a higher energy proton collider or a dedicated Higgs factory, held the potential to measure the Higgs self-coupling with unprecedented precision. This measurement is crucial for understanding the shape of the Higgs potential and, more broadly, the nature of electroweak symmetry breaking. If deviations were found in the self-coupling from what the standard model predicts, it would suggest that new physics is at play. Similarly, more refined searches for processes like di-Higgs production or the exploration of exotic decay modes could eventually reveal hidden structures, pointing toward phenomena beyond the known picture. Meanwhile, theorists continued to refine their models and proposals to account for the lack of definitive signals. Supersymmetry, SI models, for instance, evolved to account for the absence of new particles at lower energies by extending the range of parameters or introducing more complex structures. Composite Higgs models, on the other hand, offered a different approach by positing that Higgs might not be a fundamental particle, but rather the composite result of interactions among more basic constituents. Extra-dimensional theories also came into play, proposing that warp geometries might push new physics into higher energy regimes, or make it manifest in subtle and difficult-to-detect ways. Some even entertained the possibility that the universe itself is fine-tuned, suggesting that we might just happen to live in a lucky patch of parameter space that supports complex structures. Another area of investigation involved effective field theory approaches. These approaches did not assume a specific model for new physics, but rather sought to parameterize all the ways in which the Higgs couplings might deviate from the standard model predictions. By comparing these parameterized expansions with experimental data, scientists could look for any emerging patterns. Such a method allows for the exploration of every conceivable form of new physics that might be hidden at high energy scales. If any of the measured coefficients deviated significantly from zero, it could be the first concrete indication of new physics beyond the standard model. All of these efforts underscored a crucial point. The Higgs boson, while an important discovery, was only a small piece of a much larger puzzle. For decades, researchers had recognized that the standard model of particle physics is incomplete. The Higgs discovery, while monumental, did not close the door on these deeper questions. Instead, it confirmed one crucial element of the prevailing framework, but left open the more profound question of what lies beyond it. This left the scientific community at a crossroads. Should they continue to refine existing theories, hoping to detect subtle deviations, or should they boldly explore entirely new approaches to understanding the fundamental forces of nature? The tension between these two paths was palpable. Some physicists continued to put their faith in supersymmetry, which offers elegant solutions to many problems in particle physics. Others pinned their hopes on composite Higgs models, while a third group advocated for an entirely new framework for understanding the fundamental forces of nature. From a broader perspective, the search for new theoretical alternatives is driven by the undeniable fact that the Standard Model leaves crucial phenomena unexplained. Despite its immense success in describing much of the known universe, the Standard Model does not address dark matter, the origin of neutrino masses, the imbalance between matter and antimatter in the universe, or the elusive quest to reconcile quantum mechanics with gravity. While the discovery of the Higgs boson provided a vital piece of the puzzle by explaining how particles acquire mass, it did not resolve these deeper mysteries. The field of particle physics remains wide open for new ideas and insights, and each new experimental result has the potential to guide researchers closer to a more complete understanding of the universe. Someday, one of these alternative theories might gain substantial support, particularly if a surprising new experimental result aligns with it. Until that time, theorists will continue to propose new ways of extending or reinterpreting the Higgs mechanism, each effort aiming to fill in the gaps left by the Standard Model. The Higgs boson, it turns out, was merely one part of the grand story. Whether through supersymmetry, composite Higgs models, extra dimensions, or entirely new paradigms, each theoretical proposal seeks to extend the boundaries of our understanding. The Higgs provided a crucial confirmation of the Standard Model, but it also opened the door to new possibilities, inviting further experiments and theoretical advancements that could ultimately lead to profound revelations about the universe. When the Higgs boson was first proposed, it was described in the simplest terms: a scalar particle arising from a single field. Over the course of decades, this minimal picture became the default assumption in the scientific community. By the time experiments at the Large Hadron Collider began, most researchers expected to observe a single Higgs-like particle at a specific mass if the Standard Model was correct. Yet, there was always a chance that the Higgs might present itself in an unexpected form, or that the particle discovered might not be the straightforward Standard Model Higgs at all. Even after the groundbreaking announcement in 2012, when a Higgs-like boson weighing around 125 giga-electron-volts (GeV) was detected, physicists were cautious in their language. They often referred to it as a Higgs-like particle or a new boson, rather than definitively claiming it was the Standard Model Higgs. In theory, this new particle could have been just one of several Higgs states, and some even speculated that it might be part of a two Higgs doublet model or a bound state rather than an elementary particle. One of the key measurements that helped clarify the situation was the spin and parity of the newly discovered boson. The Standard Model predicts that the Higgs should be a scalar particle with spin zero and positive parity. Other hypothetical particles, such as gravitons, would have spin 2 or potentially different parity. Through detailed analysis of its decay channels, researchers were able to confirm that the new particle did indeed exhibit characteristics consistent with spin zero and positive parity. This was a strong indication that the new boson was very much like the Standard Model Higgs, but it did not completely rule out the possibility that it could be part of a larger family of Higgs bosons. In many extended Higgs sector models, like the lightest Higgs often resembles the Standard Model version, while heavier states remain hidden at higher masses. This raises the intriguing possibility that the 125 GeV boson discovered at the LHC might be just the tip of the iceberg, and additional Higgs bosons could exist at energies beyond current collider capabilities. Despite extensive searches for additional Higgs bosons, including charged Higgs particles and neutral states with different masses, no clear evidence of such particles has yet been found. However, this does not rule out their existence. particularly if their masses lie beyond the reach of current collider energies. In composite Higgs models, the observed boson could be a bound state of more fundamental particles, similar to how the pion emerges from strong interactions in quantum chromodynamics. If this is the case, the Higgs itself would not be elementary, but a composite object with its mass generated by a new sector of strongly interacting particles. One appealing aspect of this idea is that it could address the hierarchy problem, the question of why the Higgs mass is so much lighter than the Planck scale without requiring delicate fine-tuning. A composite Higgs might also behave differently in certain scattering processes or exhibit altered couplings. Experiments at the LHC have measured these couplings, finding them to be very close to the predictions of the Standard Model. However, these measurements have not yet reached the level of precision needed to completely rule out composite models. Another intriguing possibility is that the observed boson could be a pseudo-Goldstone boson, resulting from a spontaneously broken global symmetry, which would explain why the Higgs is so light compared to other particles in the theory. So far, no deviations have been observed in the Higgs boson's interactions that would suggest such a scenario. However, as measurements improve, there remains the possibility that small mixings with other scalar fields could alter the Higgs's couplings or decay channels, potentially revealing new physics. While large mixings appear unlikely, smaller mixings cannot be ruled out entirely, and future precision measurements could ultimately provide the crucial data needed to confirm or dismiss these alternative ideas. The journey to fully understand the Higgs boson and its role in the universe is far from over. With each new discovery, the field of particle physics takes one more step toward answering the profound questions that still elude us. Whether through incremental advances or revolutionary breakthroughs, the search for new physics beyond the Standard Model will continue to shape the future of science for decades to come. There were speculations that the Higgs boson might harbor hidden quantum numbers or engage in interactions with unknown sectors of the universe. This led to the intriguing hypothesis that the Higgs could act as a portal to dark matter, decaying invisibly on rare occasions. While experiments have placed limits on the frequency of such invisible decays, these limits have not yet eliminated the possibility entirely. If the Higgs were to decay into unknown particles with a 1% branching ratio, detecting such events with current data would be a tremendous challenge, leaving open the possibility that it could interact with hidden realms, perhaps revealing parts of the universe that remain unseen by conventional means. Even the concept of CP symmetry, which dictates the relationship between particle and antiparticle behavior, has been called into question in the context of the Higgs. The Standard Model predicts that the Higgs should be CP even, meaning it should remain unchanged when particles and their mirror images, antiparticles, are swapped. However, some theoretical models suggest that the Higgs may contain both CP even and CP odd components, a phenomenon that could introduce CP violation. Researchers have been particularly interested in exploring decay modes of the Higgs that could potentially reveal such violations. Although no evidence of CP violation has been found yet, this remains an area of keen interest because finding a source of CP violation could help explain one of the universe's greatest mysteries: why there is more matter than antimatter. Despite this, the data collected so far seem to support the hypothesis that the observed Higgs boson is indeed the one predicted by the Standard Model, showing no significant deviations from theoretical expectations. It couples to other particles in direct proportion to their masses, and its total decay width appears consistent with predictions. Nevertheless, the precision of these observations is not infinite. There remains a possibility, albeit a small one, that there are minor deviations from the expected behavior of the Higgs. To explore these possibilities further, researchers will need more data, perhaps from higher luminosity runs or future colliders capable of probing deeper into the heart of particle physics. The challenge is that the Standard Model Higgs was always thought to be relatively simple in its nature. It was never expected to produce extravagant new phenomena. Even if new physics lies hidden at higher energies, the Higgs could still be a low-energy manifestation of a more intricate theory, one that may become visible only under very specific conditions. Confirming this would require discovering heavier particles or measuring subtle anomalies in the Higgs couplings at a level that current technology cannot yet reach. Some speculative theories go even further. A few physicists entertain the idea that the Higgs might arise from entirely novel structures in spacetime, though such theories remain far from mainstream. Others have considered the concept of unparticles, although this idea has gradually lost traction in the field over time. For now, the available data firmly support the conclusion that the 125 GeV boson behaves primarily as a standard model scalar particle. However, another line of thinking suggests that the Higgs might act as a doorway to a hidden valley of particles. In this theory, the Higgs could couple weakly to new particles that belong to a mirror sector of the universe, one that interacts in ways that are not yet visible to us. This interaction could give rise to unusual signals, such as long-lived particle decays, but searches for these phenomena have so far yielded inconclusive results. The possibility of multiple Higgs bosons, siblings of the 125 GeV particle, remains closely tied to theories such as supersymmetry, which predict that there should be multiple Higgs states. If the 125 GeV particle is indeed the lightest, it is possible that its heavier counterparts exist but have eluded detection to date. The same could be true for extended gauge sectors or composite structures, where additional resonances may exist at higher energies or interact with particles weakly. These additional states might be part of a broader spectrum that the current capabilities of the Large Hadron Collider, LHC, are not able to reveal. There are even more extreme possibilities to consider. Could the Higgs be a spin-2 entity linked to gravity? While this idea is intriguing, measurements of the Higgs spin have ruled out this possibility. Its spin has been measured to match that of a scalar particle, not the tensor spin characteristic of spin-2 particles. Other theories propose that the Higgs mechanism could arise from a deeper phenomenon, such as radiative symmetry breaking. However, these alternative mechanisms often lead to final outcomes that look very much like the conventional Higgs particle, making it difficult to distinguish them from the standard model Higgs based on current experiments. As scientists continue to refine their measurements of the Higgs boson's interactions with various particles, such as top quarks, bottom quarks, tau leptons, and W and Z bosons, they are also investigating its self-coupling. This self-coupling governs the potential energy associated with the Higgs field. If this self-coupling differs from the predictions of the standard model, it could indicate that the Higgs is part of a more complex framework. But accurately measuring this parameter is no easy task. It requires detecting extremely rare processes, such as di-Higgs production, which are challenging to observe with current technology. So far, the available data have not been sufficient to draw definitive conclusions about the self-coupling or other subtle properties of the Higgs. All of these lines of inquiry feed into a larger overarching narrative. The discovery of the Higgs boson at the LHC in 2012 was a monumental achievement, confirming a key prediction of the standard model. However, identifying whether this particle is the exact Higgs as envisioned by the standard model, or whether it is part of a broader, more complex theory, requires ongoing and detailed investigation. Any potential differences may manifest as small deviations in the data, or they may demand more advanced technologies, such as a more powerful collider, to detect heavier particles that lie beyond our current reach. For now, the simplest interpretation is that the 125 GeV particle is indeed the Higgs boson predicted by the standard model. However, this interpretation does not address some of the universe's most profound mysteries, such as the nature of dark matter or the reason for the imbalance between matter and antimatter. Alternatively, the 125 GeV Higgs could simply be one piece of a much larger puzzle. This could involve multiple Higgs-like particles, composite structures, or entirely new hidden sectors that we have yet to explore fully. The data collected so far have not ruled out these more exotic possibilities. Since the discovery of the Higgs boson in 2012, increasingly precise measurements have further strengthened the case that the 125 GeV boson behaves as the standard model Higgs. If any deviations exist, they are minuscule, barely detectable within the current data. Some scientists worry that the Higgs might remain exactly as predicted by the Standard Model, leaving larger unresolved questions about the universe's most fundamental aspects. Others remain hopeful that, with enough data, subtle discrepancies may emerge, revealing that the Higgs is only one piece of a far grander theory, one that could ultimately provide answers to questions about dark matter, the origin of the universe, and the deep structure of reality itself. Could the Higgs be something else entirely? While this remains a possibility, it has yet to be proven, and the future of this quest remains full of tantalizing unknowns. The possibilities are vast, and the story of the Higgs is far from complete.